classical turbulence goes. Now, for the quantum turbulence, I will, okay, this is another one that Luca Marconi wrote. On the quantum turbulence, I will take my comments essentially from another PhysRevX article by Giorgio Krustolovic and his colleagues, Intermittency of Velocity Circulation. All of this has at its base this long paper written by Sasha Migdal in Physics Reports. It's about 117 pages long. Um, Basically, what is at the bottom of this is the fact that Sasha noticed the analogy between characteristic function of circulation in turbulence and the Wilson loops in quantum chromodynamics, and he deduced a number of very interesting results. And this is the part that I will focus on. I consider especially and only one aspect of it, known as the area rule, simply because we don't have time. What area rule means is that the statistical properties of circulation in a turbulent flow, whether it is quantum or classical, depend on the area of the loop, not on its shape. For example, simplistically speaking, I take a square here, which is loop A, and a rectangle here, which is loop B. The circulation characteristics of the loops A and B are the same as long as they circumscribe the same area. This has something important about turbulence itself, which we will discuss if we have time later on. So that's the part of this work that I will describe. Now, for testing some of the concepts, I use data which is numerically generated of isotropic turbulence in a periodic box. The periodic box has a grid size which varies from 512 on the side to 8,900, 1,992. And there were also some simulations on 16384 box, but we haven't used those data extensively simply because they are very expensive to manipulate. So the second column I have noted here is the so-called microscale Reynolds number, which is the square root of the actual large-scale Reynolds number. So the large-scale Reynolds number is of the order of a million or so. More importantly, the ratio of the large scale to the small scale in the flow, which is the scaling range, which gives you some idea of the scaling range of the problem, is given in the third column. And I will talk about how the quantum turbulence data were generated a little bit later. So what one does is now is to inscribe many of these loops, rectangular, all of them in the so-called inertial range, that is the scaling range that we have just discussed. And the area of the loop is large enough. That's 38,400 eta squared, where eta is the smallest scale. L1 and L2 are the dimensions of this rectangle, and the aspect ratio of this rectangle varies by factor 2 in the simulations that I am describing here. What is plotted is the circulation on this horizontal axis, normalized by the large-scale circulation, and on the vertical axis, the probability density of the circulation. Each symbol here represents a rectangle of a different aspect ratio. You can see that to a very good approximation, these data all collapse on top of each other, even though the aspect ratio varies by a large, well, relatively large number like 20. And what one should do is to note that for very low probability of the order of 10 power 9 or so, there's a huge variation among different contours. And of course, it's falling off here, but the probability is so low that we should probably discount them for the present purposes. So that is one point, that the symbols all collapse on each other. And the second is that there is a red line here, which is coming from Migdal's theory, which is essentially the exponential modulated by 1 over square root of the circulation. This did not come, by the way, in Sasha's theory um, in a vacuum. It was deduced on the basis of experimental results, going back and forth several times between um, simulations and the theory. Now, what you find from just this graph is that, in fact, maybe the area rule is a very good result. And what is plotted in the inset is the same result for Gaussian random noise in 3D, but you take planes of it. So now, but you may want to look at it a little bit closer. After all, are these data points really collapsing in each other, on each other, or is it just a good approximation? Can we say something more concrete? So here on this graph, is shown the area of various loops. I have shown you here. I have to pull this down here. Uh, the kind of loops for which these are computed, there are two loops here, both of them having the same area, one is a square and the other having this aspect ratio of 4. Now, there are two sets of symbols here, and plotted for both of them is the variance of the circulation. That is, you have these contours at different places in this field of turbulence, and then you take and square it, and then you take the average, and that is what is plotted here. So the mean square of the circulation as a function of the now I see something on chat. Maybe there is a question. Um, no, there is nothing. So, okay. Let me go back. Cancel this. Um, Now, what you find is, again, the two symbols collapse very close to each other, collapse on each other nearly. And the slope of this line is area to the power 2/3, which is the classical results of Kolmogorov turbulence. So in fact, you might say that the two areas have identical characteristics, but also the result is that of Kolmogorov turbulence. If you actually draw the least square fit, it is, as we said in this caption here, the slope is 0.674, which is only 1.2% or so different from Kolmogorov results. I will come back to the inset, which has an important point to make. But let me now go to another aspect of it, and that is, instead of the kind of contours I have just discussed, suppose I have a contour like this figure 8 loop. So I start from here, let us say I go to my right and up, etc. So the area is to my left, and then I come back here and go this way. So the area is to the right of me. So if you want to take the vectorial area of the total loop, then of course it would be the difference between the two areas. If I want to just sum them up scalarly, it would be just L1 squared plus L2 squared. The question is whether in the area rule, whether the circulation now depends upon the scalar area or the vector area, for instance. Now, you can make a very simple case that if it is scalar area, I just give you the entire logic in this one line, then the circulation, the mean square circulation will go like 2/3 power of the area. If, of course, it is to be the vector area, then it will go like 1/3 power of the area. And you have already seen that it goes like area to the power 2/3. I show this again here. And so it is far from area to the power one-third. So it is the scalar area that matters, which one can argue on a number of other considerations as well. As the area of the loop becomes very small, as to the left of this picture, then the mean square, the root mean square, the standard deviation of the circulation will vary linearly with the area, as it should when you are in the viscous range, that is the fluid dynamics or turbulence dynamics is controlled by viscosity. If you go to very large areas, as to the right top, then the result sort of falls off from the scaling relation. And in fact, that's what you saw, although I didn't point out to you earlier in the previous diagram as well. So obviously, it needs a better scrutiny, but for now, we will assume that the scalar area holds and the shape of the contour does not matter. So I can only consider simple squares henceforth without compromising the results. I'll go back to this insight that I had promised to talk about. Again, the two symbols corresponding to these two loops fall on top of each other. But actually, if you take the point by point area, point by point ratio of these two symbols, as I have plotted here, the variance, the root mean square of one divided by the root mean square of the other, plotted against the area. If, of course, the two symbols were identical to each other, this ratio would be unity. It is close to unity, but it is not, as you can see. In fact, for two Reynolds numbers, 240 and 1300, this is the so-called microscale Reynolds number, which, as I pointed out, is the square root of the big Reynolds number. You can see that higher the Reynolds number, this range increases, but again, the ratio is not exactly unity, but is slightly different from unity. Now, that's one aspect to remember. The other aspect to remember is that actually you can write down the variance of the circulation around a contour in this form, where Vi and Vj are, let's say, the velocities at the points I and j in the contour. And this is the two-point correlation function of turbulence. This is a kind of function that everybody knows in many other circumstances. Now, this two-point correlation function in general depends upon the properties of turbulence at points I and j, and also depends upon the distance between the coordinates r and r prime. So let's say, for instance, we agree to dismiss the dependence in front, but we will say that it depends only on the distance between the 2 points, and it has a power law relation like this. Suppose that is the case. Even if that is the case, the integral is not the function, is not just the function only of the area of the rectangle. As you can see, it depends upon the differences in some detail. So in particular, this is not the case unless we have here this alpha is 2/3 when I have this going like the difference distance divided to the raised to the power 4/3, which is the classical Kolmogorov results, which presumably is universal. So only in that case can we expect the properties of the circulation to be independent of the area entirely. So in fact, you can put in here the measured two-point correlation function and calculate this and plot it as a function of, this is the quantity that's plotted here, the root mean square, and for an area which is 3,840 eta squared, you can measure the aspect ratio by this ratio L1 plus L2 by eta, where L1 and L2 are the two sides, and I actually compute this, then I get these numbers. And in fact, if I put in a theoretical results and compute that integral, I get this, which is the same more or less. And again, you can see that it's really not exactly independent of the aspect ratio, although it is close. It is something that varies very slowly, but it is not exact. So there's a 10% variation, they point out. Now, if alpha is half, for instance, as Migdal speculated might be the case, then of course this is very easy to compute, and then it goes like area itself. There is no dependence of anything other than the area. Thus, if alpha is half, the area rule is completely compatible with it. Now, Migdal didn't really have a theory for this, but as I said, this is for the variance of the circulation. But for higher moments of circulation, that is p greater than 2, where I didn't say what p is, but p is the power of the circulation in the average. In analogy, he just said, well, it'll go like r to the power lambda p. Well, lambda p is linear in p. As you can see, lambda squared is r to the power 2, which is the area. Therefore, he said, well, everything else will go in the same fashion, and it will be p, except that you might have finite Reynolds number corrections. So his argument was that some of the deviations we see here are simply the finite Reynolds number corrections, which is a point I will test a little bit further down. Now, the contours that I have discussed so far are in the plane, in a 3D turbulence fields, that you take a slice of it and you circumscribe your contours on it, and you compute your properties, then you have another slice, etc., etc. Now, suppose I now want to go to 3D contours. Now, what sort of things can we do? Here is an example to the left of a contour in 3D, C1, as I have described, which is one area like this, a square, r squared here, and then attached to it, perpendicular to it, is another one like that, which is r squared. So it's like a gate in soccer games, for instance. Now there are many types of areas that are possible that circumscribe this contour, but then there is the minimal surface that one can think of. After all, the planar areas that I have described are minimal surfaces on the plane. So now, if in fact there is some authenticity to the area rule that is only depends on the area and not on the shape, etc., it shouldn't depend on the dimension either. So whether I take a planar area in like the ones I've described, or I take a minimal surface like for example in this example that you can actually compute as we have computed here. So then what I should do to test this hypothesis is that I should look at what this minimal area is, and it happens to be 1.78 r squared, where r is this length. And I should go to a plane and take a planar loop whose area is also 1.78 r squared, which means its side is 1.33 r. So now I compute the probability density of the circulation and plot it on this axis and the amplitude of circulation on this axis. And what you see is that, in fact, the two are not the same. One is for 3D and the other is for 2D. I don't remember which is which, but there is no question at all that there's a difference between the two. So I have already pointed out the approximate nature of the area rule, but this one certainly seems to suggest there is more to it than just the area. So should we just abandon the area rule as one of the several approximate results, or should I should I consider some other circumstances for which it is actually more true than these results suggest? So to do that, let me compute higher order moments of the circulation. I plotted here pth order moment of circulation in a square of linear size r, plotted against r, normalized in some fashion. So p is 2 gives me the variance and etc. So I have computed for 2, 4, 6, and 8. And if there is any scaling at all, these quantities must be linear on a log-log plot. And I have shown here the results for p equal to 2, 4, 6, and 8. Instead of drawing straight lines in a log-log plot, what I have done in the inset is to take the local slope of these lines. And if in fact they are power laws, then the slopes would be constant. So local slopes plotted against the size, the linear size of the contour. This is for order 2, 4, 6, and 8. Now, what is plotted on the vertical dashed lines are the limits of the scaling range in the current simulations. And so if in fact there is scaling, I should expect horizontal these results to be on line horizontal line. So in fact, you can see for order 2, it's pretty nearly so. And in fact, the line I have drawn is really the Kolmogorov results. So for order 2, it's not only scaling, but also Kolmogorov. I go to 4, it seems to scale perhaps a little bit less well. And the Kolmogorov result is a little bit above the mean line I can draw through this data. For the 6th order, perhaps less so, but still tolerably good. And then it is more to the south of the Kolmogorov results. And this trend continues for the 8th order as well. So I'm saying this all to evaluate the area rule further, and the moments of circulation scale well, and higher exponents fall below the Kolmogorov result. K41 simply means Kolmogorov 1941, but not by much. Excuse me. Plotted now in this graph against the R moment order P. Sorry, was there a question?
Somebody just called.
Okay, then let me continue. I must have given you the cue to
Can I
cough.
just ask,
Yeah.
since you self-interrupted, so if I understand correctly, the upshot of comparing flat, if you like, planes versus this curved plane is
Yes.
that you get a completely different, or you get a noticeably different histogram distribution. So is there a sense of curvature being important there?
So let's make that.
Curvature versus not. And I want to understand the difference between flat and that minimal surface curvature is one of them, but yeah.
Let's take that as a tentative conclusion that in fact they are different, but I will modify that result in the next slide or two.
Okay.
That's the point of this whole exercise in the last couple of slides. Just to go back, so where we are. So I have this p-third moment of the circulation of size on a contour of size r, and the slopes of them I call lambda p, and I plot these lambda p here against p for various p going from, let's say, -1 to 10. So the -1, the minus part here refers to the absolute value because otherwise you get some nonsensical results. So that's the reason for the symbol on P. In any case, even if you ignore that, the point is that as a function of P, this lambda lies on a linear relation that I have shown here, which is which is this dashed red line, which is the Kolmogorov line. And beyond about the third order or fourth order or something like that, the data deviate from this Kolmogorov line and plot on perhaps another line, which has a deviation from the Kolmogorov result, which I call delta lambda by this vertical line. So I call attention to this in several different ways. One of them is, if you take me literally on it, on my calling, then the results fall on two fractal sets. One, which is this one here, and the other characterized by this line. Each of them have different uh, dimensions, fractal dimensions. This one here is space filling because it lies on the Kolmogorov result, which is space filling. And this one here is a non-space filling set whose dimension you can compute from the slope of this line. It's not important for our discussion, so I will not say what the number is. So we called it bifractality. That was the title of our paper. The circulation resides essentially on two fractal sets. As far as low order moments go, it is a space filling set. And as far as high order moments go, it's on a non-space filling or a fractal set whose dimension is some number less than 3. And the other thing is that remember Sasha's result that says that these exponents will go linearly in P. And of course, the linear relation, I've shown this by short line. And in fact, it doesn't take very much convincing to say that this is quite departing from this linear relation. Perhaps if I had much higher relation, the results may fall on the linear relation, but we think the results or the Reynolds numbers are high enough that it is unlikely for that to happen. So that's one aspect of it. The other aspect, why this might be very interesting, if you're interested in scaling exponents and things like that, is the normal scaling in turbulence. If you take velocity increments over a linear size of r raised to power to p. So the pth order moment of the so-called structure function delta ur, then Kolmogorov relation would say p by 3, which are the relations I had used before. And we know from a number of measurements made for many years, there is in fact anomalous scaling. It doesn't go like p thirds, but goes like r to the power zeta p, which departs from p by 3, except for p equal to 3, which is a special case. And these zeta p have a much different characteristic from the lambda p that I've computed. In particular, they're not linear or fall on two linear sets like this, but is a nonlinear relation and which demands that every order moment has to be understood on its own merit. Unlike here, where low order moments have one characteristic. So if I understand one of them, it is pretty much the same as all the others. And high order moments would be very similar here as shown in this other fractal. Right? And now I come back to the relation result you've already seen. That is the probability density, or histogram as you called it, of the as a circulation against the magnitude of circulation itself. And the two lines here, one is for the 3D contour and the other is for the 2D contour, both of them having the same area. As we already pointed out, the two are in fact different. However, you can do one other thing, and that is since there is the bifractality in the circulation property, if I'm interested in, let's say, low order moments, then instead of plotting the circulation itself, I plot circulation divided, normalized properly for m equal to some low order number like 2 or 3 or something like that. And the result you see is this. My expectation is that since low order moments come from around the mean of the probability density, the two must collapse on each other well around the part that contribute to low order moments. If on the other hand, I'm interested in high order moments, I should look at the other line of this bifractal. Let's say I have here done the same for some high order moment like 6 or something like that. I forget exactly what that is. The expectation is that would collapse again, the data, and in fact, you can see that it does pretty well. So in fact, the area rule is that for each fractal set, it is very nearly correct. But if you try to mix the two of them, then it is not the right representation. So this is about the classical area rule. Now let's talk about quantum turbulence. Quantum turbulence was simulated using the so-called, I'm reading the caption here, generalized GP equation, Gross-Pitevsky equation, simulated on a 2048 grid. Now, it generalized in some sense, that is, it adds a couple of terms to the standard Gross-Pitevsky simulations. And these authors have assured me that, in fact, this generalization is immaterial for the results I'm going to describe to you. So it might well be Gross-Pitevsky simulations. So this is the results of these vortex lines that you can see in this box. And you take a little segment of it and you enlarge it, and you can see these vortex lines, quantized vortex lines. And if I take a slice of this, what you see is the one on the right. So there are here red dots and blue dots. Blue indicates one sign of quantized vortex lines, and red indicates the other one. So in fact, you can see some are red and some are blue, etc. Now, if I want to calculate the circulation around contours, squares in this instance, as we have always done so far, it depends upon the size of the contour, as you can see. For example, here is a small contour of the order of, let's say, the diameter of the quantized vortex line, for instance. And depending upon whether it circumscribes a red vortex line or a blue vortex line, the circulation around the contour will be kappa, which is the quantized quantum of circulation. Or it may be, if it is somewhere this vacuous region, it would be 0. So you can actually compute what the circulation is just by counting all these things and knowing how many of these vortices there are. If, on the other hand, the contour is bigger, as I've shown here, then it encompasses a number of these vortex lines. And what happens to those circulations depends upon how these are clustered together. So now let's take a look at the probability density or histogram in this particular case against the circulation itself. R here indicates the size of the box, and the box size is of the if the circulation is if the box size is very small, as I said, the circulation has a very finite chance of being 0, as you can see from here. So in fact, what you see is that the probability density is centered around 0 for small box size. And if you go to the left or right, essentially they are the same, symmetric. Then you might have some that are 0 and some now finite circulation in them. And these are the size of the boxes. Here, size of the box is 0.1 in these units, which is the, let's say, intervortex spacing of these quantized vortices. So that's what you see, discrete circulation around small contours. Of course, if you go to big contours, then the probability density is again a sort of essentially a continuous line, as very similar to the lines that you saw before. So let's look at the results of the variance. Let me recall that plotted here is the area of the contour divided by some normalization landscape, which happens to be just the intervortex spacing squared. Plotted here is the mean squared of the circulation. And these orange lines are for the classical turbulence, and these are for the quantum turbulence. For the classical one, I'm just recalling what we found earlier. We had something very close to 4/3 in this region, which is the scaling region between, let's say, a small scale and the large scale, and very small scales, which is dominated by viscosity. It goes like the square of the contour area, which is a very simple result you can deduce from just a very simple arguments. For the classical case, there are two types of results. Again, one for very small areas or small contour size, which here compared to let us say the intervortex distance, it would be a square root of about 0.3 or something like that. And below that, you have one result, and you have one result above this. Now, above this demarcating region, you have area to the power 4/3, which is the classical Kolmogorov result, as I have been talking about for some time. Now, why is it a classical Kolmogorov result? It's because when the contours become large, then they circumscribe many of these vortices, and there is some kind of polarization taking place that is clustered together, or vortex lines of a given sense. So in fact, what you see is that for large scales, these polarized vortex lines essentially behave like big structures in classical turbulence. So I have the Kolmogorov result. And in fact, associated with that is a whole phenomenology resulting in minus 5/3 in the spectral density, and all the other high order moments and anomalous scaling, etc., which I will not delve here into. And very small contours. As I said before, for the smallest one, you can actually calculate what this is just by counting where they are, and this number simply says how intermittent these structures are. And it's very easy to show that, again, you have a random distribution of points in a box with sign which may be plus or minus 1, for instance. As you know, in quantum turbulence, the circulation is quantized. So you will get this a to the power 1 relation. So that's what you find. And for the higher order moments, which is pth order here, p equals 1, 2, 3, 4, 6, 10, etc., plotted against the area. Again, you have here again two separate regions. One, the range that is dominated by quantum properties of these vortex lines, and this other which tends to classical behavior. And for the quantum range, these odd moments go like r squared or L squared independent of p. And here they depart for each p, it is a different result. So what is plotted here is this lambda p, which is the slope of these lines. In the quantum region, it is constant for all p equal to 2. And for the classical regime, you have the similar result, that there is a scaling in the classical range, so to speak, and there are the Kolmogorov results, and the results fall just a bit below the Kolmogorov results. What is plotted here is lambda p as a function of p. Recall a very similar one that I showed for the classical results. For small p, they fall on the Kolmogorov line. And for p greater than a certain number, which we can talk about in detail if one is interested, they fall again on another line. So the bifractality that we mentioned earlier for classical turbulence also holds for quantum turbulence. There is the, I think this is a very interesting results as well. So that's about sums up my set of results on the area rule. Two conclusions to remember. The area rule is recovered because of bifractality of circulation observed in both classical and quantum turbulence. And discreteness of quantized vorticity has an effect for small boxes, but features of classical turbulence appear for large boxes. So thank you for your kindness and for inviting me and listening to me.
Quick question.
Yes, I have a question, which is a follow-up to Vadim's question.
Grisha, can you mute yourself because there's too many microphones active?
Okay, so you.
This is Grisha Falkovich. I know Grisha very well.
Yeah, okay, so if now I'm talking, because I mute mine, okay. As a follow-up to Vadim's question, when you compare circulation distribution.
1 second, I have to deal with this. 1 second, I'm gonna turn off this microphone. Go ahead.
Yeah, mine is mute now.
Yes.
Just mute your microphone.
Unmute mine, okay.
Yeah.
You compare two probabilities for planar and non-planar contours, and you rescale by one factor, and they did not fail, and you choose this factor from minimal area. They still seem very similar, so maybe there is some other factor which you can find empirically, by which you can rescale one distribution into another.
Yeah, the one that made best sense to us from the point of view of these results is to go with the way I have normalized here, basically fractal scaling. But there may be other ways, and I should think about it. Yeah, I will in fact think about it once I go back.
Yeah, can I make it, I just watched a YouTube video on non-Euclidean geometries, and it just seems like just designing surfaces that have controlled curvature that's
Yeah.
uniform, like spheres.
Yes.
If you can just project on spheres, maybe that would be the uneasy.
Yeah,
Anyway.
it's just computational things become very complicated. And I'm sure there are many important things to do, as we should do, in fact.
We move on. All right, let's thank the speaker again.
Okay, thanks again for having me. Grisha, I will stay on for your talk.
Very good. I think you can stop sharing because Grisha will bump you off.
I will stop sharing momentarily.
Wherever you want to say it.
Um,
Wherever you're comfortable.
Okay, I have
Main
stopped
thing is-
sharing now. I will also mute myself.
Okay,
So
so
now
now you share. If you go to, where is the share screen?
share screen,
That's what we've been doing.
and that's my thing. And
And
then now
if
have
you really want
slide.
to use this thing, you can, let me turn on the light.
Remember that it's always covering this,
No, I think people
I
have
wanna
figured it out.
make the slideshow.
Yes, so if
Here
you
is my
go, 1
PowerPoint.
second, so if you go nope. 5, and now we have to kill this somehow.
Okay,
And now we have to get rid of this. Somewhere down here. Is this good?
do we see it on the screen? Excellent, okay.
The
fantastic.
only issue is that I don't like that floating. I have to.
Yeah. I don't see, I don't have it.
No, you don't see it there, but we see
On
it
screen.
here, and so.
Well, there is nothing really of
No,
informational value in the lower bar.
well, okay,
Mhm.
if you don't mind, then
Okay, good.
it wasn't here yesterday. That's.
Uh-huh.
Yeah, I'm
So
not-
what I have half an hour?
You have 45 minutes, but if you do it in half an hour, then we'll have 10 minutes and.
Yeah, okay, I'll do it in 40 minutes. Good.
It's up to you.
So, I wanna, when I chosen a subject, so I've decided not to talk about some present work, and it will be covered by other talk, but I'll try to give a more or less classical content, and I've chosen a subject which I think is more interesting for diverse group of people. And if we look what could be interesting for different people, for quantum, classical people, and condensed matter, and field theorists, and fluid mechanicists, it usually boils down to some very generic properties of turbulent statistics, mostly symmetries. So I've decided to give you an overview of classical results of symmetries, which are here and which are not here, and particularly focus on a couple of problems which aren't solved, even though I believe they're very clearly formulated for quite some time. Problems of theoretical nature, and which essentially means that there is some empirical material which is more or less clear, and it has totally zero explanation. So just a general setting, I'll start from a usual three-dimensional turbulence in which we have some kind of a large-scale steering. So we generate turbulence on this large scale. Our Reynolds number is supposed to be large, which means that there is a huge interval of scales between the scale where we excite the system and where we dissipate. And so from a general viewpoint of physics, we're dealing with an extremely non-equilibrium situation. There is no fluctuation dissipation. You force at one scale and you dissipate at another, which is totally opposite to equilibrium, where you force and dissipate at every scale and it's in balance. Okay, so in this respect, Reynolds number for fluid mechanics this means one thing, but for statistical physics, it means just degree of non-equilibrium. And so in this sense, we generalize the idea of turbulence as a far from equilibrium state of any system. Could be spin system, nothing to do with fluids, but as long as you generate on one scale or in one frequency and you dissipate in a very, very different frequency, so you have many, many modes in between which are far from equilibrium, that's what we call turbulence. And I think that this general perspective is very, very fruitful when you look from this viewpoint. So you're less fluid now and you're more general physics content. Okay, so even though we start from this typical fluid situation, we'll have in mind more or less a general setting. We are far from equilibrium. Many modes are far from equilibrium. The number of modes is our Reynolds number. And so now we ask what is, because it's statistical, strongly fluctuating system, we look at its properties of its distribution. So let's say that we are now still talking about fluids, but again, this could be, I don't know, fluctuation of magnetization or whatever. So we have some quantity which fluctuates, and we also have some scale. And the scale, as in Shreni-Stock, is supposed to be in between the scale of excitation and between the scale of dissipation. So you're inside this turbulence region. In terms of scales. So you may ask, what is the probability distribution of this quantity? And let's for simplicity take it as scalar, namely take a longitudinal projection of velocity difference. So I have 2 points at the distance r. I measure velocity here, I measure velocity here. It's 2 fluctuating quantities. I take the difference, I project on this line. Bingo. I have a full function of a single scalar and the vector. And I start asking what are its symmetries. For example, if it's time reversible, then it would be the same with reflecting delta V. Now I'm asking if it's isotropic, whether it depends on the direction of R. Then I start to ask if it's both is true, and this is just a function of 2 scalar, can I present it as a function of their ratio taken in some power? That would mean that it's scale invariant, or some people more likely to say it's monofractal. Okay, so that's more or less basic questions. And then again, well, maybe a short remark. Turbulence means many things for different people. Like it's a domain in which meteorologists, engineer, let's say chemical engineer, physicists, mathematicians, they meet, but they generally have kind of different approaches to it. And it's surprisingly that the first major advance in understanding turbulence came from 2 opposite ends of the spectrum. The idea was of meteorologists and the mathematics was that of mathematicians. Namely, there were Richardson and Kolmogorov, kind of almost 100 years ago. So the idea was the idea of a cascade. It was a statement, if we really excite at a very large scale and we dissipate at a very small scale, and in between for intermediate scale, we can kind of forget about dissipation because it's happened at a very small scale. Kind of forget about forcing because it happened at a very large scale. It's like a conserving system. So we expect the energy conserving system just to transport energy from scale to scale. And then we can do a very simple estimate. We can say that this delta V at a scale R squared is the energy of a vortex of this side. You take velocity here, take velocity here, this vortex give you this difference, you square it, that's its energy. You divide it by a typical time, which in mechanics is always distance divided by velocity. And you say that this must be energy transfer rate, and you expect it to be R independent. It immediately gives you this Richardson-Kolmogorov scaling. And first of all, it really, because it's delta V here and delta V here, it's a third moment. So you expect the third moment to be non-zero. There is nothing here about its sign, but it immediately tells you this time reversibility is broken. If you have a third moment of velocity, then your statistics is not invariant with respect to t minus t, v minus v, whatever the sign of epsilon. Now, the sign of epsilon is essentially which direction your cascade go, from large scale to small or from small to large. At this point, it's not set. And now, out of this very general hand waving, Kolmogorov actually derived, well, Kolmogorov didn't derive this for arbitrary d, but this is what you do if you do what Kolmogorov derived. And his derivation was pretty straightforward. You just take Navier-Stokes equation at one point, multiply by velocity at another point, average, assume that as viscosity goes to zero, the system has a steady state statistics. It's a very strong assumption. Mathematicians, 100 years, almost 180 years after Kolmogorov, are still working on it. There are cases in which you can more or less argue that this is the case. But if this is the case, then you derive this law. Okay, that's essentially the statement, which is physically kind of very, very trivial statement. It says that, look, you pump energy at large scales, right? And then it goes to smaller and smaller and smaller scales. Imagine Fourier space. So in Fourier space, you're at a very low K, and you have a cascade going. And as the viscosity goes to zero, it's like this pipe in the Fourier space. You're getting it longer and longer and longer, but it still carries the same flux. So it doesn't matter where you actually burn it. It's still the same flux, and you expect that as it goes, it has a steady state. And of course, it's, as Polyakov likes to say, is the first example of anomaly. 10 years before Schwinger, Kolmogorov did it, or to other field theorists, even before Pauli, kind of arguing about it. It's anomaly in a sense that your time reversibility breaking factor is viscosity. Viscosity goes to zero, energy dissipation rate goes to inconstant. When viscosity goes to zero, that's what we call now dissipative anomaly. Good. Let's move forward.
So can I make
yes.
a comment? And I don't want to, I'm learning lots, I don't want to distract you. But in physics, generally, one of the sort of assumptions is that there is a separation of scales, which you're using it implicitly or explicitly, that the short distances and large distances cannot be connected in one step.
Yeah.
But there's no locality in Fourier space. So this assumption must be a dynamical.
There is a locality.
Yeah,
this is, well, maybe Vladimir or some of his collaborator will talk about it, how it's in a way too, but it's a locality which is totally necessary in the sense that if you look at the Fourier space and you ask whether the interaction of three modes with a comparable wave numbers and three modes with one wave number with two very large and one very small, then you expect that the second contribution will be much smaller. Nobody can prove it for Navier-Stokes, but we can prove it for wave turbulence in a kinetic equation, namely in the zeroth perturbative approximation. And then what we do with Vladimir and with other people is you can go to next order and see how it's actually broken and whether you can do resummation. But locality is totally crucial. Absolutely. Yeah. And okay. Well, yeah. So now again, when you look at this relation, it's instead of delta V, because now it's a vector. So essentially, Kolmogorov relation also could be written in this way. But then you realize that this epsilon, this escape, could be in different directions. And then particularly in 2D, you have extra invariant, which is vorticity. In 2D, vorticity is a Lagrangian invariant. This is just transported by flow. Vorticity squared is also invariant. So you cannot burn energy at small scale. It's vorticity burned at small scale. So energy must go upscale. And essentially, the statement is that this third moment has a sign depending on dimensionality, namely it's negative in 3D and it's positive in 2D. It means a very simple thing. It tells you that your average velocity difference between 2 points is 0. There's kind of no preferred direction. So what it means that your third moment is positive or negative. It means that when you have a strong fluctuation, and the strong fluctuation is predominantly like this, that your third moment will be negative. And this is a direct cascade. Namely, you have a strong somehow vortex or whatever, and preferably it has a negative longitudinal velocity difference. And then with Sasha Zamolodchikov, we derived a operator product expansion generalization of it. So now you can, this is a statement about third moment, but 2 point. There is velocity difference between 2 points. Then one may ask, could we somehow split, because there are three velocities involved, can we split 2 points and say something about 3-point correlation function? Again, as opposite to many field theories, we cannot prove, but we can assume that such operator product expansion exists and then derive some consequences out of it. And as later you will see, it will be important for proving that there is no conformal invariance in turbulence. So what we did with Sasha, we derived these 3-point moments out of Kolmogorov relation for 2-point moments, and there is some kind of other interesting relation. It's actually hidden some for that, but it's okay. It actually tells you what if you have 3 points and you measure velocity difference, what will be the difference between this configuration and that configuration. And in 2D, kind of here velocity will be predominantly in this direction, predominantly in this, and in 3D it will be opposite. I don't want to go into this geometrical details, but what I'm saying is that the simple idea of a cascade can be put into at least few exact mathematical statements about third moment, 2-point third moment, and 3-point third moment, and it could be actually checked numerically. Now, yes, Volodya.
It's an OPE, which points are getting taken close to each other? You got R1 or 2.
Yeah, so I take velocity at point 1, velocity at point 2, and velocity at point 3. Okay, and I'm computing correlation function, and it's of course expansion in this small distance relatively to this small.
And you think the OPE exists or doesn't it?
We assume that it exists, derive consequences of it, and then go to and check it empirically. And you'll see in a moment how in 2D it kills conformal invariance in a bubble. Okay, so now let's go beyond third moment. And as you've seen in Shlini's talk, again, this assumption, which if this would be true, because we know third moment and it scales linearly, would mean that h is 1/3. And of course, there are exponents. There is our review with Srinivasan in Physics Today, which is kind of a popular review. And here is again taken from this review with Srinivasan. This is a difference between exponents and naive monoscaling prediction. For the third moment, it is 0. Here is this point, right? But for moments less than 2, it's positive, and larger than 2, it's negative, which means a very, very dramatic statement. So as long as your exponent is not dimensional, it means that the ratio between r, your distance where you measure velocity difference, and box size or pumping scale L enters. And it enters in a positive power here and negative power here, which means that when L goes to infinity and you keep given distance, you keep the same energy dissipation rate, namely your third moment is fixed, your distance is fixed. Now somewhere at the edge of the universe, your box scale increases and increases and increases. Then your second moment, all moments less than third go to 0, including spectral density. So you keep the energy flux. All moments higher go to infinity, all moments lower go to 0. It tells you the turbulence statistics is getting more and more intermittent as you keep here locally energy flux and just increase the box size. Which means that the same cascade, the same rate of energy transfer is realized by more and more rare, but more and more violent fluctuations. That's a very simple message from here. That's what anomalous scaling or multifractality means here. Yes.
Doesn't this immediately indicate the LP won't converge? Because it means you don't have scalar variance, so in general, the LP doesn't converge.
Yeah, you don't, right. It means that your OP in the usual general setting wouldn't work. But on the other hand, in a moment we'll go to 2D, where this is not true, where we have a monofractality and scalar invariant, and there we use this OP. So which tells you that in 3D your OP is actually not very relevant, but in 2D it's still relevant. That's a very good remark. Okay, good. So now when we try to understand this multifractality, multi-scaling, we ask ourselves, what are those numbers? What is this number? 2 here, it's 2, okay? So there is some number for 2. Yeah. What is this dumb number? It's not Kolmogorov 2/3, which I would guess from simple energy cascade. What is this number? Does it have any physical meaning? What it tells us, and one of the things that we made sense out of it was made in a much simpler problem, and that was a problem of so-called passive scalar, but it's essentially something about turbulent diffusion and how fluid particle means. And in the next slide, I'll return it back to velocity. So we ask the following question. If you have, let's say, few fluid particles, and they just go away with time, they just, randomly wander, you may ask statistics related to this particle, and particularly, you may ask if these distances between them generally grow, and for turbulence, this would be A equal to 3 cube, it's super diffusion. The Richardson law, which corresponds to Kolmogorov scaling, you ask, can I find some functions of distances which is of a non-zero, let's say, positive uniformity? So it's proportional to some power of R, and yet it does not change. At this point, this very general and very powerful idea of martingales or statistical conservation law enters. So you ask if some quantities are on average non-growing. They would be telling you something intimate about your statistics. And of course, for general usual thermal diffusion, you can find such martingales. They're just harmonic polynomials, which they turn Laplacian into 0, and Laplacian is your evolution operator. Turbulent evolution is a little bit more complicated. It's a kind of a diffusion in a curved space. Still, you can find this conservation law, and we computed them for some very simple model of velocity field. And the net result was the following. The physics is pretty simple. As long as you have not 2 particles, but let's say 3 particles or 4, you have a geometry. So you can build a function of distances and angles, so that as time goes, increase of distances compensated by the decrease of angular correlation. And so on average, it doesn't change. But now the scaling of such conservation laws very intimately depends on your space dimensionality, on the statistics of your velocity field. And essentially, this law is what determines this anomalous exponent. And just very briefly, I'll tell you, projecting this idea back into velocities. So again, this is the velocity difference between 2 fluid particles at a distance L. And this is this distance as a function of time. This is longitudinal, this is U at a distance R. Namely, now I take 2 fluid particles and follow them in time. And I measure this velocity as a function of time. And I'm asking, can I build a conservation law which would compensate of increase of this generally with time by the decrease of this? And the answer is yes. I'm not going into the details, but you can find such function f, and it's asymptotic at very large distances would be behaving as some power law of the distance, for which this is a conservation law. And this is exactly the same exponent which determines the second moment of velocity if you just take a snapshot and average over all fluid pairs, as we say, Lagrangian average. So on this language, we related these anomalous exponents to the Lagrangian conservation laws. Not that we can derive it, for example, for three-dimensional incompressible fluid flow, because we don't know the statistics of velocity. But we can guarantee that what you measure when you measure second moment of velocity at a given time, and what you measure when you find the conservation law of Lagrangian pair evolution is the same number, and it was checked numerically. Okay, so this is our way to make sense, and it is maybe useful to comment that this use of conservation law in statistics is kind of opposite to what we get used in dynamics. Noether theorem in Hamiltonian dynamics tells us that the moment you have an extra symmetry, you have a respected conservation law. In this case, we have a statistical conservation law, and there is infinity of them, which breaks this monofractality exactly because every conservation law imposes its own exponent. It tells you that there is more to turbulence than flux and cascade. Only third moment of velocity difference is determined by the law of energy dissipation or by this dissipative anomaly. Every other moment is determined by a very non-trivial geometrical conservation law, which is, we call it zero modes. All this was 3D. And now, the remaining 7 minutes, yes.
Can you think of what the conservation laws are? You have an infinite family, but what's the end conserved quantity?
At every moment, there's a different conservation law, which is built out of velocities and distances, and it compensates increase of the separation of particle by the decrease of angular correlation. They all are geometric.
This is your inside of polygon.
This is our marking. They don't have dynamical meaning. This is statistical geometry. Okay? So what the statement is that every higher and higher moment is determined by the statistical geometry. This scaling is how fast triangle forgets its shape. This how quadrangle forgets its shape. So you took this with this aspect ratio, with time it forgets it and go into a square, right? On average. So this scaling tells you how fast it happens. And it depends on number of points. Okay. There is much more to turbulence than dynamics. This is essentially the statement. Yes,
Is there a way, so in the same sense that the flux can be visualized in Fourier space as you started, is there a way to recast these statistical conservation laws in Fourier space?
No, I don't know. No, absolutely not. It's so much about geometry of a finite number of points.
But it sounds like, because if it's a local conservation, I'm just thinking of just Fourier transforms. If it's a hyperlocal conservation law, that means that it is actually connected.
Let me kill your dream at the very beginning. The fact that you can talk about Fourier space, it's because in incompressible fluid, your conserved quantity is quadratic. So you have Parseval theorem and you can put it. You go to compressible turbulence where your conservation law rho v squared, already non-quadratic, forget about Fourier space. There is no meaningful spectral density of anything.
No, I was actually trying to kill your separation of scale between, because if the conservation law is local in space and nonlinear, that means that the conservation law is actually connecting different parts of.
Absolutely, and that's why this geometrical zero modes, law, they bring anomalous scaling, which means that you always remember about your large scale.
Okay.
That the conservation law is a way that no matter how many steps of cascade passed, you still remember some moments. And that what we find with Vladimir is that actually in the wave turbulence also there are some things which no matter what you do, you keep nonlinearity small, you increase box scale, you remember how many steps of a cascade you passed. Yeah, conservation law is a way of memory. Exactly. Okay, good. So now just last few minutes, I want to tell you good news. So there was a bad news, there was no symmetries, everything was broken. Well, what now is
By the way, you actually have time. You
Ah,
have
yes, okay.
15 more minutes.
so there will be more good news then.
Okay.
So what I now do, I go now to inverse cascade. Namely that as we discussed in 2D, there is usually extra invariant, which is also quadratic, and it's something which is related to higher derivative, to the derivatives of velocity, means that in Fourier space, it's something which dominates over energy at large wave numbers, and so it is what is actually burned in the direct cascade, so your energy goes upscale. And what is good now, and now I'm formulating what I believe is a very clearly formulated and totally unsolved problem, which I spent 3 years trying to solve it, and I asked other people. There were also, I mean, Polakov tried to, there are many good people, I mean, better than me, who tried to solve it and didn't solve. So I'm trying to tell it to next generation, maybe they will solve it. So here's the problem. So first of all, I may look at the Euler equation for velocity just by taking curl of it, introducing vorticity. Then Euler equation just has this simple form in 2D, and my V again in 2D because it's incompressible could be introduced to stream function. So I have two scalars now: stream function, which determines velocity, and vorticity, which is pseudoscalar. Okay, so now I can relate it. Here is omega is supposed to be. So if for Euler equation, my stream function is related to the vorticity, just the Laplacian of stream function is a vorticity. But I can introduce it in a little bit more general setting, and it's a family of fluid mechanical models, which many of them has clear physical sense, and they're applied in different domains. So I consider A, which is Lagrangian invariant. It's transported by a fluid. It's not dissipated, it's just transported as long as there is no viscosity. I have my stream function, and they are related by some kind of a linear general relation where M is a parameter. So I have a family. Euler equation M equal to 2, this turns into logarithm, but there is surface quasi-geostrophic model where inhomogeneously heating large scale motion of the atmosphere are also very important. But there is a highly magnetized plasma or very fast rotating shell of water, which corresponds to M equal to -2. There is a family. And mathematicians are playing a lot with it, and meteorologists are liking it. If you're a condensed matter person, you may think about it as a charge density and the field, and then again changing dimensionality in a sense changes how your Coulomb law look like. This is a very, very similar by the relation of just Coulomb law in different dimensions. Somebody
Something happened to your share. You wrote the share screen.
well, just I went dark.
Oh, I think you ran out of juice.
Wait.
Give you a charge.
I didn't expect it because it was fully charged.
Maybe the Zoom.
But you have electricity.
Say again?
You have electricity.
We have electricity
Yeah.
somewhere.
I ran out of it, but you do.
Let's see if they're.
Okay. I apologize because I'm not sure that. Yeah.
See if it turns on and I'll hold. Okay.
Okay.
See if your thing turns on.
Yeah, in a sense, I can tell the rest on a blackboard if necessary.
If necessary, but.
Mhm.
Whatever it's called.
Okay, well,
I hope it's okay if I stand.
no. There's something.
No,
Well, first of all, I can move it like this, and you can probably put it down. Okay. But
something else falls down.
yeah, you know, I
Okay.
is I think that because it does not appear here.
You need to put your pen in.
Yeah.
No, it's not typing. Just click on that
Okay.
and Let's see if it's.
We can have a Ludip version. I can just switch into Blackboard. No, I think that would probably take too much time. So let me tell you the rest of the story on the Blackboard. We can
Turn this off. Sorry, I forgot how to, oh, right.
So now I look at this family of models, and it has each one of them has some two quadratic invariants. One is energy, and another is kind of vorticity or analog of this invariant, and which means that they all have inverse cascades. Okay, and this inverse cascades is again, as we discussed, if you take delta V cube, this is just epsilon r, and in the 3D that was negative and this is positive. This is the only difference. Or you can look at a vorticity on a scale r cube, and it's also proportional to some r in the power minus 2/3 related to it. Okay, so you may again ask the same question. If your probability distribution, let's say of omega on a scale r and r, could it be presented as an omega r divided by r in the power minus? It was probably well 2/3 q minus 2/3. And what you discover empirically, and nobody were able to prove it, that all these inverse cascade are monofractal. Namely, that they all, if you divide what is called naive Kolmogorov, Richard Kolmogorov scale, something which is based on a flux law, then your probability distribution is monofractal. And then you ask if it's possible, then it's also conformal invariance. Namely, that this scale invariance is local. So you can really look at your turbulent field, stretch it here, compress it here, but go analytically smoothly from one, just keeping angles, right? So could your statistics survive such kind of transformation? And then what we proved with the logic of using our OP, that a 3-point correlation function, omega 8.1, omega 8.2, and omega 8.3, just because there is a third, this is something like third moment 2 point. This is the 3-point splitting of this relation. But as long as this is, if OP works, then this is non-zero, you can derive this. So we can derive this, and people numerically check that this is indeed what we derive, and it is non-zero, no matter what is specific shell. And then it somehow kills conformal invariance as a property of a bulk vorticity, because you can, this is a pseudo-scalar, you cannot find a conformal field, at least not of any type of minimal model or reasonable set in which this quantity would be non-zero. Because a conformal invariance very strongly restricts certain moment. It's a 3-point moment, is very, very, and Polyakov tried for a very long time to cook out something which is kind of would give this moment, and it did. So at this point, kind of was a feeling, okay, so there is just a monofractal, but there is nothing behind it. And then a very interesting new language came out, which is called SLE. And my late friend Christoph Deletsky, actually, I owe it to him. He told me, you need to learn this new language, which was, he was much more mathematical than me. So, and because he's an older friend, so I've learned this language. It's a beautiful language. It's again geometry. As again, another friend, like Leo Kaderman says, the interesting thing happened when geometry means physics. So the idea is called SLE, and this is Löwner. It was Karl Löwner, German mathematician, who invented a way to encode a curve into the motion of a point on a line, on a straight line. It's called Löwner evolution.
his idea was as follows. Let's say I take half plane and I have a curve in a half plane. And I have t, which is the coordinate along the curve. So let's say up to this point, I can make a map from a half plane minus this curve, just treat it as a slit, right? So it's a part of a boundary into just half plane. This is some map which depends on z and t, because as t goes like this map changes. And so the tip is a part of the boundary, is mapped into the boundary. It's Riemann theorem, right? So as you go along this curve, this point moves along a straight line. It's called Lerner. It's a very powerful tool which mathematicians, and it's 100 years old. And then Adel Schramm, which is S of this, again, unfortunately, was killed in the mountain accident. With Adel, we started together with Weizmann at the same time. So Adel suggested to look at this, when this is just a simple Brownian walk. This is just a Brownian motion. So zeta of 0, zeta of t, mean value of it is 0. And this is just some kappa t. Kappa is dimensionless number. So in this, everything is kind of properly normalized. And then you realize that when now everything is characterized by this quantity kappa. As kappa is larger, this is kind of a more and more random curve, right? And there is a natural boundary kappa equal to 4, which corresponds to this curve not being a simple curve, it starts touching itself, etc. Okay, so this was a limit. And then what Schramm proved, and several of his students, all of who got Fields Medal, but Adel did not because he was like 40.5 years old when he published the main paper on the subject. They proved that the statistics of this curve is conformally invariant as long as this is a Brownian. Okay, and I remember I felt ecstatic when I learned it because for me geometry is very difficult, but random walk is what turbulent fictitious do for living, right? So the moment that I started to translate all this, let's insert operator there, which I never understood, into the simple language that if you have a Brownian walk, which means it forgets itself on every step. That what translates into local spelling variance here. And then all statistical physics, all integrable model that we knew fell into this language. Namely, if you ask what is the statistics of domain lines in Ising model, this is just kappa equal to 3. If you ask what is the statistics of a percolation cluster, I'm just listing, critical phenomena and universality classes. If you ask what is a percolation cluster, and percolation, this is important, and this is what in a moment appear, is that if you have a landscape and you start filling it by water, if this landscape is sufficiently short correlated with height, is sufficiently short correlated function, then there will be a boundary between what is filled by water and what is dry land, and this is the called percolation cluster. It corresponds to kappa equal to 6, etc. So because I've run out of time due to my, I now just formulate the result. So for all this family of models, again, let me remind you, you have a psi function, which is a stream function, and you relate it to some Lagrangian invariant by some dr prime in 2D. You have a family of models. For each one, you have an inverse cascade. For each one, if you look at lines of 0, isolines of 0, A, you get an SOE with a respective kappa. And in particularly, when you look at earlier equation, is Kolmogorov scaling, and in inverse cascade is an exact Kolmogorov scaling. It's a monofractal situation. You have kappa equal to 6, which is the, you can say, kind of a simplest universality class. It's a zero charge conformal field theory, which describes statistics of zero vorticity lines. And it's not esoteric quantity. If you look at our atmosphere, the zero vorticity line, it's a boundary between cyclones and anticyclones. Right? So you have a And it's where it rains. It's a very interesting line. And the meteorologists are very much interested in the statistics of this line. And we know now a lot about statistics of this line. You can take a Carby formula for probability of this line going into rectangle and coming out of there, and you can use it for, well, our planet is not that large, so that we can have a big interval of scales. So I want to end here. So what I want to say is that somehow in this inverse cascade, in the whole family of it, we have an emergent, totally unexpected conformal invariance, which does not work in a bulk. It only describes a zero lines, which are very important. In a sense, zero vorticity for Euler means potential flow, which is kind of trivial, totally determined by boundary. So zero vorticity line is what remains from this potential flow. Nobody was able to relate this to this. This is why it's so clearly formulated for mathematician that it's really, you have fluid mechanical equation and you have geometrical constructions based on this SLE, and they somehow related, and nobody knows how. So let me finish with this puzzle.
I'll just quickly ask for clarification. So is the statement that for each M that you listed, empirically there is a corresponding kappa?
Yeah.
And the other question is that when you made a point that conformal invariance is broken in the bulk, but there's still scaling to it.
Yes. It's
Did
a
you know?
monofractal, but there is no conformal invariance for a block. There are many interesting, I mean, John Cardy was a referee of this paper in Nature, so he made us to run through all tests possible. So it's
Good, all right.
Right, I'm a little bit confused because you said there's no conformal invariance, and then over here you said we were.
there is no conformal invariance for the bulk field. You have omega, right? It's a bulk field. You compute multiple correlation factors, they are scaling up. You look at the line of zero vorticity. There's only one sector in your statistics which is conformal invariant.
I think you just misspoke. They're not conformally invariant, but they are scale invariant in the bulk.
Omega's a bulk field is scale invariant. It's monofractal, but it's not conformal invariant. My lines are scale invariant and conformal invariant. You can associate conformal theory with these lines, as long as you only consider points on this line. Okay? This is what remains in turbulence out of what you would, in critical phenomena, you have bulk scale invariant, bulk conformal invariance, and also, you know, domain walls in Ising also conformal invariant. Here only lines. Yes.
So there's also these conformal loop ensembles that are generalized or they lead to the bulk, so we also see that.
Which right we did not find anything related to it. So this all about a single line, right? This soup, we did not find anything related.
Any, other questions? All right, let's thank Grisha and go to Swati. Okay, we'll resume in half hour or so. I'm gonna stop the recording. Somebody's clapping. Excellent.
I unmuted.
You should disconnect from audio.
I believe I'm good. Yeah,
No, I'm not sure. Let's see.
Let's see.
Question of how many, excuse me.
oh, I see. Yeah, please.
Wait, okay, sorry, I don't wanna do.
Oh, you,
Interrupt you.
no, you're okay.
Just a second. Here, that's what I'm looking for. See where it says leave computer audio?
Great.
Otherwise,
So
there's
now
gonna
there's
be
no
echoing.
chance that, got it.
Well, there's always.
Oh, but you're spoiling my,
No, I don't want to, yeah, oh, sorry, I didn't mean to do that. One thing I wanted to do is
Yeah.
figure out how to remove that floaty thing.
yeah, I know. It's not a big deal. I've had lots of,
All right. Never mind. If you don't mind,
no,
does
no.
anybody know how to get rid of this floaty thing?
I'll click that and see.
Yeah,
view on the top right.
Yeah,
Show panel maybe?
No,
Or that's
That
probably
you
the
already did
opposite.
it. You wanted to hide that.
I wanna hide that, yeah.
It should just go by
Okay.
itself. with the mouse.
Well, it didn't. Standard immersive, nope, I don't wanna, no. Hide self-view.
Oh, this looks good.
It's gone. I think
It's gone.
You just have to like give it a moment. to cool down.
Okay, I'm just gonna step away before I make things worse.
No, you're fine.
You move the mouse.
Okay, it's gone, excellent, I didn't know what I did, I mean. All right, let's, we're only 4 minutes behind schedule, it came back, what did you do?
Well, I moved the mouse out of the way because it was distracting Aaron.
Okay, I think now we're moving from the world of dead liquids to world of liquids that are alive.
Yeah, well, liquid is the strong word, but
It's a strong word.
okay, well, yeah, thanks for having me. This is first time I give a talk like this. It's a real kick for me, so hopefully you find it enjoyable. Yeah, I'll tell you about a theory called flocking, which is hilariously a pretty famous theory in condensed matter physics, which is not something that I would have expected. And I just want to shout out all my collaborators. So in particular, Eli is just wrapping up his undergrad degree at Brown, and he has many competitive graduate offers. So keep an eye out for him, try to recruit him and all that. He's outstanding. He was with us for one of these research exchange summers. And Marvin, I believe, is starting his postdoc at Chicago this fall, so another person to look out for. Aaron is a postdoc at Boulder, and Andy is my advisor. And our manuscript will appear shortly. There's a few calculations that we're wrapping up, and I'll tease those near the end of the talk if there's time. I should say I feel that the talk is pretty short. I think I have 45 minutes, so feel free to interrupt me with questions, and I'll do my best to answer those. Okay, so let me begin by introducing the subject by showing you a video of some really nice birds. These are birds somewhere in Canada, which is where I grew up. And yeah, so we see some collective motion. And indeed, even in 2D, which 2D birds, you know, well, maybe the surface of the Earth is roughly 2D. Even in 2D, though, models of self-propelled spins that have short-range interactions seem to show some long-range order, collective behavior. But in 2D, for short-range interactions, we have Mermin-Wagner theorem that tells us we should not expect long-range order in 2 dimensions. And in fact, provably, this will never happen, right? So what's going on? So let me give you a taste of some of the literature that's tried to get at this question. In particular, I think it started in roughly 95, where Viksak and many other authors whose names are not known came up with an off-lattice microscopic model for spins that move. And then later that same year, Toner and Tu wrote down a phenomenological field theory to describe the same system. And as recently as 2011, I guess Toner was still working on this problem. So he studied something called Malthusian flocks, romantically named Malthusian flocks, which are ones where the birds can die. So in effect, you have a constant density. So you only have to keep track of the velocity field. So this is another effective field theory, but just for the velocity field.
If they can die and have constant density, you must have some births as well.
Yeah, you can have births as well. Yeah, sure.
Fly, they're like you go to the flag.
Yeah. That's it. No. Amusingly, the terminology people use, "death on the wing," is what people say in the title of some of these papers. So
No, that's easy to believe, what about birth on?
yeah, I know, but look, you do your best, right? Anyway, I guess something that I've always found puzzling about this model in particular is that they're claiming long-range order, but they're keeping around some degrees of freedom that have finite lifetime. So really, like if you had some Goldstone mode, you'd think that in a true effective field theory, the only degree of freedom you'd have to keep track of would be some angular variable telling you the direction that the birds are flying, the direction of their collective motion, yet they keep a longitudinal velocity as well. No big deal, but that's going to motivate sort of what I'm going to talk about when I talk about our work. Okay, good. And then most recently, there's this really nice PRL from that was published in 2022 that shows that some non-perturbative effects that are very subtle can actually destroy the long-range order that Toner claimed in 2011 for this model of birds giving birth and dying on the wing. So that was sort of what got us interested in this model, or in this problem, I should say. Maybe there are non-perturbative effects that you have to be really careful of. Just really complicates the story. And that's all I'm going to try to do in this talk. I'm not claiming to have a theory of flocking or anything like that, obviously. But I do think that we can complicate the story in some non-trivial ways, and I'm interested to hear what people think.
That's a
Yeah,
very,
please, Woody, yeah.
good question. So, it seems like, in this slide, you're, focusing on 2D and there is a puzzle. There's a question mark.
Yeah.
Now in 2D and for finite size flocks, I would then wonder, can one really distinguish, or does one even care to distinguish long range order, quasi long range order? Are these
Well,
U1 spins, or is there, do we even we only expect quasi long? I guess what I'm trying to say, there are finer questions which seems like, given the size of the flock, I'm like, who cares, right?
Yeah.
There may be more interesting questions.
I'm with you. I think whether one cares may be a matter of taste, but yeah, to get to my punchline, yeah, maybe I'll just do that, and then
That's
if
fine.
you have more
We'll,
questions,
insert
we'll
later.
yeah, let's do that. So, oh, okay, and this is another great reference for this problem. Yeah.
Is that where you're from?
Yeah, I grew up in Halifax. Yeah, that's right. And I never talk about it though. So.
Are you bird watcher?
I was a bird watcher as a kid. Yeah, I love my iPad background is some nuthatches in Nova Scotia. So great. Okay, so let's get on with the temptation to be too cute when discussing this topic is overwhelming almost for me. So okay, so let me now give you the punchline of the talk, and then I'll dive into the motivation for the rest of the talk. So what I'm going to present is a model with classical two-component spins on a 2D square lattice. And I'll keep track of only the orientational sort of order parameter or degree of freedom. And the log wavelength description, which is technically non-hydrodynamic by my definition because nothing's conserved in this model, but the long wavelength description is going to be identical, almost identical to the model that Toner has studied in 2011. And in particular, it has this form. So the terms that are supposed to be in blue, I hope it's showing up, are kind of convective looking term that tells you that birds want to fly in the direction they're pointing, that spins want to propagate in the direction that they're pointing. And then on the right-hand side, we have the yellow terms are is just a normal diffusive piece with a Gaussian white noise. Yeah. And what's doing a lot of heavy lifting is the order gradient cubed terms that I put in white on the left-hand side. And my claim is that at long times, you can write down a probability distribution for all of the theta degrees of freedom, which living on a lattice or in continuum, whatever. And we've shown that it's exactly the stationary distribution Hamiltonian for a thermal XY magnet. Yeah. In particular, what that means is that there's no true long-range order. Quasi long-range order, fine. But provably, since it's a 2D XY model, this theory has no long-range order. So we found a theory of flocking, at least one lattice model for flocking that seems to not have long-range order, and we can prove that. So in the rest of this talk, I'll give you some details of this. And the reason I want to go through the details and motivation is, it's a workshop. I think that this will prove to be an instructive example of the line of thought that my advisor, Andy, has introduced to us yesterday. So I'll review that along the way. And then I'll try to argue to you that even though we have a stationary distribution that's featureless, essentially in this way, almost featureless XY model, that we still have a non-trivial dynamical universality class. And this is not so unexpected if you know anything about the KPZ 1D equation. Yeah. Okay, any questions before I dive into the physics here? Yeah, please go ahead.
Feel free to defer if you're about to say these things.
Yeah.
But order Napa cube, is that a third derivative or a derivative cube?
Third derivative.
Okay, so this is linear and, oh no, it's not linear, right? Okay.
This is still non-linear because of the blue things.
Yeah, and so this is.
And we could have more non-linearities too, lots of more irrelevant things, yeah.
Toner to unit velocity.
This is Toner 2 with a unit velocity, yep.
Plus y.
Yep, that's what I'm saying. This identical to Toner 2 if the longitudinal velocity has already relaxed, blah, blah, blah. Yeah. Good enough? Great, okay. More questions before I... Okay, so with that, I'll move in. So let me just remind you about this idea of time reversal symmetry that we were introduced to yesterday. So let's start with some classical degrees of freedom, which for me are going to be these spins that are going to interact with the thermal bath. If you look at a true microscopic description of a model like this, you'll find that you have time reversal symmetry because you have a bunch of Newtonian particles bouncing around and hitting each other, right? F equals ma, time reversal symmetric. But when you coarse grain by integrating out the bath, you get a stochastic equation that looks something like this. So rate of change of one of your fields is equal to what I'll call a force. It's a force in the sense that I guess Aristotle understood it. And we'll have a Gaussian white noise in this case as well. And I just need to specify the variance of the noise. So I'll call it a constant Q that will just become a delta function shortly. But the point is that this equation doesn't look like it has time reversal symmetry as we were told yesterday. But we can make it have time reversal symmetry, or at least understand the consequences of microscopic time reversal symmetry on this coarse-grained macroscopic field theory. And the way to do that is first we want to think about the Fokker-Planck equation, which is completely equivalent and which I'm parametrizing in terms of a differential operator W. And this Fokker-Planck equation may have a stationary distribution. So in the limit of t goes to infinity, set the left-hand side to 0 and maybe try to solve. But for us, we'll start with this stationary distribution and look at things that are consistent with that. I'm free to call it e to the minus phi if I want, in analogy with thermodynamics. And of course, for this model, I'm going to postulate. So we're going to start by saying that we want that stationary distribution to be a thermal XY model, as I previously motivated. And then the result that I'll just claim and not prove, but it was discussed a little bit more in a little bit more detail by Andy yesterday, is that this dissipating theory is compatible with microscopic time reversal symmetry, which also goes by the name detailed balance if the following transformation holds on W. So you take W, you take its transpose, like in quantum mechanics, in the sense of a differential operator, and then you multiply and divide, you make a similarity transformation with the stationary distribution itself. This is what time reversal symmetry means for dissipative theory. In this sense, the diffusion equation is time reversal symmetric.
Means that your steady state is kind of equilibrium.
Yeah.
It's kind of zero flux in the probability space everywhere.
In the limit of infinite time, you have zero flux in probability space everywhere. Yep.
Because then the question will have different solution too.
Yeah,
Different fluxes, yeah?
Sure. That could be so. Yeah. So we're going to look at, it's an assumption for us that we reach a long time stationary distribution. Now you could ask, okay, could stationary distribution be non-local, blah, 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 have high body interactions? Sure. But for us, we'll take this nice local guess and derive consequences. Yeah. Okay. And then, so this transformation of W implies the following relation for this force F. So the first piece, which is the only one that happens if Q, the noise, is constant, this is nothing but time-dependent Ginzburg-Landau theory, right? So this is like gradient of free energy is proportional to this Aristotelian force. And this Q, since it's a noise variance, needs to be symmetric. Yeah. So from a model building perspective, what's the most general symmetric matrix you can write down, or maybe the simplest, depending on whatever you want to do. Okay, so in this model, I'm going to take Q to just be a delta function. So we'll have uncorrelated noise. This is physically relevant for something like a thermal bath. And just for the rest of the talk, I'll also define mu. It's kind of like a chemical potential as the gradient of this free energy that I've defined, where the free energy is this phi thing, which is the stationary distribution. In this case, from the previous slide, Lanchevins equation looks like this, which in the continuum limit up to higher order corrections with more gradients is just a diffusion equation. Yeah, so that's the time reversal symmetric part of our dynamics, the dissipative part of the dynamics for this model. This is just time-dependent Ginzburg-Landau theory. I'm really not saying anything new here, but I don't need to tell you that. But next, I want to talk about what happens when we break time reversal symmetry, because for a model like something like flocking, we actually don't have time reversal symmetry. Birds don't have time reversal symmetry. Basically, the bird's flying this way and you reverse the arrow of time. Now they're flying this way. You need to also rotate the birds, right? And that's how you get time reversal symmetry. So I drew some cute pictures. So you start with the bird, a bit of grouse. I didn't want to be too ambitious with this model. The grouse is a silly bird. So you start with a bird going up in this direction. If you flip the arrow of time, now it looks like the bird's going this direction, but it's still pointing the first direction, yeah? So then you need to both rotate the bird and rotate your spatial axes kind of in a diagonal kind of way. And I've called that, just to confuse you, I've called that P. I guess I'm used to saying PT, but it's not, I don't think it's quite parity. And then you actually do have a true symmetry. So this at the microscopic level for an active thing like birds, this is the symmetry that we need to enforce, not just T, but only PT. And that's what's going to allow us to write down more terms. So what if we want to include terms that are odd under time reversal? If we write down something odd under time reversal and odd under this P, then we have a nice symmetric term. Well, it's almost exactly the same as what we did before. So take transpose of W, multiply and divide by stationary distribution in the similarity transform. Now we just allow ourselves to put a minus sign on the left-hand side. So now we say that the Fokker-Planck generator, W, it's allowed to switch sign under this sort of detailed balance transformation that we're calling time reversal symmetry. Let me just finish the slide and then happy to. So at this point, we get kind of an analogous constraint on what F has to look like if W is going to be time reversal odd. So the second term that you can see, if this anti-symmetric matrix V were constant, this would be a lot like time-dependent Ginzburg-Landau theory. You have an anti-symmetric matrix, though, now instead of a symmetric matrix, which was the noise variant. But the term that's going to do a lot of heavy lifting for us is actually this case where V, it's a nonlinear theory. V has dependence on the field. And so this dB, which is derivative with respect to theta B, if I didn't introduce that notation, this is going to do a lot of heavy lifting in giving us our theory of flocking. But now let me answer Ben's question. Yeah.
So in the active matter literature, people often talk about non-reciprocity, and this actually has to do with breaking of PT.
Yes, that's right. Yeah. So yeah, because I think I have time, I can digress a little bit on this issue of non-reciprocity, and we can talk more after, or you can, even worse, you can read our paper. But we've applied this same idea to understand a lot of non-reciprocal phases of matter, most notably these odd solids and odd fluids that are popular in Chicago right now, the group of Vincenzo Vitelli, William Irvine, etc. These pop out naturally from this formalism. The idea, just for people who don't know about non-reciprocity, is if you have a gas or maybe a fluid, maybe foxes and rabbits or something along these lines, they don't interact reciprocally, right? Because the rabbits chase the foxes, but the foxes, sorry, it's the other way. The foxes chase the rabbits, but the rabbits run away from the foxes. In that case, you do not have time reversal symmetry, even at the microscopic level. Play arrow of time backward, it looks like rabbits are chasing foxes, which doesn't make sense. Yeah. The only symmetry you have is if you reverse arrow of time and also change every fox into a rabbit and every rabbit into a fox. But if you enforce that symmetry, then we're able to understand, if you enforce that symmetry in this sense at the dissipative level, then we're able to understand a whole zoo, pardon the pun, of non-reciprocal theories. So let's talk more after, but I'll move on with the birds for now. More questions while I've interrupted myself? Or?
Actually,
Yeah, please.
so accommodating.
Yeah.
When you say understand, since I'm not knee deep in these exotic or whatever fluids, to me, understand usually means that you have a Gaussian theory that's relatively kind of like there are no anomalies that I don't understand.
Yeah.
But then I can do something with a epsilon expansion, something like this.
Yeah,
to
yeah,
understand interacting behaviors.
Sure.
I have not noticed that next step in like other non-trivial collective phenomena. By collective, I really mean non-Gaussian.
Yeah, I know what you mean. I think I'll do my best to convince you that there are such effects at the end of the talk. But if you're still not convinced, then we can talk more. But yeah, Tom. Yeah, that's right. That's right. So, for instance,
Find a field that is one or the other.
yeah, that's right. And of course, we heard in the talk by Seth yesterday how a magnetic field is one way to get this Hall component of viscosity. But there are other ways. For instance, if your particles are something dumb, like they're made out of spinning robots, you can also get this same viscosity. But we have this theory that's kind of, maybe what I mean by understand is we have a theory that's almost agnostic to the microscopic details as much as possible. Okay, let me move on. Oh.
VAB is the same as VAB in the first term and the second one. Can you generalize when there are two different antisymmetric? Yeah,
Here?
it must be the same.
Must be the same.
I see.
Must be the same in order to guarantee this
Yeah.
property
Yeah.
holds.
So
Yeah.
cancel, yeah.
Yeah. So, and let me just emphasize before moving on to the next slide that what we're really doing here is adding what I would call active or odd terms, time reversal breaking terms that still maintain the same stationary distribution. So they do not ruin the long time equilibrium-ish behavior of this model. We can have active matter that still has an equilibrium distribution. Is it all of active matter? We're not sure, but probably not. Or at least probably some active matter requires a horribly non-local stationary distribution. But we can talk more about this point. I'm not fully sure of the answer. We're very new to the field of active matter, but okay. I'll move on now and actually write down the lattice model that I promised you for flocking birds. So the point is just to pick a VAB that makes the Fokker-Planck generator Hamiltonian kind of for this, some Hamiltonian for the system, invariant under the combination PT that I previously introduced. And here's the answer. So I'm switching this A, B notation for R prime because these spins sit at various lattice sites. I need to write this down. And effectively what's happening is that rotate.
Pointer here.
Oh,
With your finger.
it's more natural.
Oh,
Is
okay,
that I think it's clear what I'm.
Good.
So when you switch the let's see, when you make a shift on the theta field, kind of at every point in space, it's kind of undone by the shift of the delta functions that comes from rotating your spatial axes. So that this is a nice like covariant thing, and it leads to a W that flips sign. Then the point is to compute this term dBVAB minus VAB UB that I wrote on the previous term. That gives you the term that appears in your Langevin equation. And you find the following equation of motion for theta, very complicated, but we can take a naive continuum limit and we find simply this convective piece up to orders and gradient. What's remarkable though is that this equation of motion, if you are careful about continuum limit, there are no corrections that are quadratic in gradients, only corrections that are cubic in gradients. So you expect that these are irrelevant compared to whatever maybe Gaussian fixed point that you're at. And I'll get to that more, but the corrections to this equation are smaller than diffusion.
Because it's odd, it couldn't have quadratic.
Exactly right. So maybe it's not so remarkable, but it's important. Maybe important is better word. Yeah. Okay, any more questions about this slide? It's really a technical slide. Good. So now we put both parts together, and as promised, we get this theory that I advertised at the beginning of the talk. And the rest of the talk, I'll just be exploring some consequences of this theory and trying to make sense, and then maybe I'll be a little bit ambitious at some point if I'm provoked. But and I'll just say one more thing, and then I'll answer Carolyn's question. But I just want to just show you one simulation that we've done, and I'll show you more later. Just to convince you that there is some kind of flocking behavior. I mean, it makes sense. It's a convective term, yeah. So no one's going to be surprised. But okay, on the left, so we have time going down on the slide. On the left, we have XY model, totally thermal model, equilibrium model. We initialize some perturbation to spins and nothing happens. On the right, the spins move roughly in the direction. They try their best to move in the direction that they're pointing, but really they move at the average spin of the average direction of the whole theory. So sorry, Carolyn, I interrupted you, but no, I'm not claiming that. No, it's the simplest one I could come up with, but we don't expect it's the only one. No, and in fact, we have many different discretizations. If you like, you can just think that the same continuum theory can always have many different discretizations.
Right, so then would the like continuum limit be the same?
Yes. We believe so. Yeah. Yeah, you put in the noise, well, roughly by hand. But I mean, if you're at a finite temperature, if you're studying a model at finite temperature, you always need such a noise in order to make time reversal symmetry manifest at the level of the coarse grain equations. Yeah.
I mean, if I start finding temperature, but I'm not in contact back, do I really have those?
Then you're not at finite temperature, I think.
Have effective noise on the code brain.
Yeah. Well, sure, that's one way to think of it. You could think, I mean, maybe I'm not saying anything mathematically sophisticated, but coarse graining, the noise kind of parameterizes the information you've lost, the errors you could have made when. I hope that helps. Let's talk more later. Let me move on because I'm a little, this is taking, it's not gonna be as short as I anticipated. So let's move on. Okay, so the first thing that we did was make one check. I'm claiming that the stationary distribution is the same as XY model. What that means is that all equal time correlation functions, 2-point functions, should agree. And that's exactly what we find. So okay, I've confusingly called the two traces equilibrium and active. Equilibrium means XY model, thermal XY model. People in the literature, for some reason, call this an equilibrium model, even though you can be out of equilibrium in that, but okay, I get it. But so, okay, the traces collapse. Maybe the colors are hard to see, but it doesn't matter. The traces collapse. So yes, our model has the same equal time correlation functions. Yeah. Yeah, sure. Whoa. Can we split the difference? Yeah. Oh, perfect. Okay, great. Yeah. Great. Okay, so now you can see the lines. I think the colors are still difficult because I like the black background, but okay, good. But what's more interesting is if you move beyond equal time correlation functions. So my claim is I'm going to try to show you some data to convince you that despite this unchanging stationary distribution, adding these blue terms that violate time reversal symmetry gives you new dynamical scaling, new dynamical universality classes. As I advertised at the beginning of the talk, this is not unexpected. For KPZ equation, KPZ fixed point in one dimension, steady state is Gaussian and featureless. Yeah, yet you still find a non-trivial dynamical universality class. So this is not something to be surprised by, but I'll show you some data to convince you that this model is an example of that. I think probably the word you should take issue with might be universality. I may have found a class, but how universal is it? That's something that we're working on. So you need to study a time-dependent correlation function to distinguish from the XY model. And the one that you want to look at, okay, I'll write it with this equation, but I'll show you what it is in a picture. What you do is you take some initial spin, and then you follow it in the direction that it points, because that's the direction you expect it to move, right? If it's a flocking bird. And then at a later time, and at some distance, you measure its 2-point function with that spin. So this is a time-dependent and space-dependent correlation function. But for some technical reasons, we like to project out some other things as well. So don't worry too much about this, but all we're doing is projecting out some rotational invariant components to make sure that we get something that's going to vanish exactly for the thermal XY model. So this is the best way that we're going to be able to distinguish our active model from the equilibrium XY model. Okay, the next few slides, I'll show you some numerics simulating the exact lattice equations of motion. So with all derivative corrections technically incorporated for this, but before another question from Ben. No, it's fine. Yeah.
So if you haven't had any questions, you can memorize it near to
Yeah.
Some modes and their velocities now.
Yeah.
You can if you look at the and you look at correlations along the velocity of sound.
Linear? No, we're going to measure this without any linearization necessary.
I mean, to do the theory of correlations.
To do the theory of correlations, yeah, one could do this. I mean, I think even in that regime, this thing would be a difficult thing to calculate by hand. I mean, I tried to do it with using this Martin-Sugia-Rose path integral, but I sort of gave up, and we're happy enough with the numerics, but let's chat at some point. Yeah, I hope that helps. Okay, so let me now plot this F correlator. Okay, so here's the first plot. Hopefully the traces are visible. So on the y-axis, I'm showing you this correlation function that I defined on the previous slide and I'm at fixed times as a function of like the distance between the two spins. And the different traces are showing you various times. So, okay, why does the peak move as you increase time? Because the birds fly, right? So that's what we're seeing in this nice plot. And then what do you think is gonna happen? Little data collapse. So we're pretty convinced. I mean, we're doing some more work, but we're pretty convinced that we see this nice data collapse if you scale both time and space together. This is the normal kind of
So F was-
this is just, let me, this is the normal dynamical critical exponent, I think, on the bottom, and it's roughly 0.4, but we're still nailing down what that is. Sorry, but
show the definition of that.
yeah. Let's go back. No, that's fine. Yeah. Yeah. Just leave it for a second. People want to take a picture. And in the meantime, I'll ask a question, answer a question. I guess to some degree, you never know for sure in this kind of numerics, because we're simulating the stochastic equations. We're not doing Monte Carlo. So in some sense, you never know. But I think the fact that if I go back and show you the equal time correlation functions, these are exactly what you can show that they have to be for an XY model in thermal equilibrium. So we're pretty sure that we've at least the probability distribution has relaxed to the stationary distribution that we expect. Yeah. Vadim.
Your data collapse, were you going to show a contrasting data collapse for the equilibrium? You know what that is? Because it's a quasi-long range ordered state, so it'll have some parallels necessarily.
Yeah, I'm not going to show that, but that's right. There's a T to the something. Yeah.
Depending on the noise and everything.
Yeah.
So, but is there?
And ours will be slightly different because we have Gaussian noise, not derivative correlated noise. Yeah.
Right. So how different is this from the whatever reasonable equilibrium?
This is different. XY model just should go down, but we could look at some.
I see. Oh, right. Yeah.
Yeah.
Uh-huh. So,
Well, actually, this F sorry, I might have even misspoke. This F thing is exactly 0 for the XY model.
That's what I was looking
Yeah, sorry. Yeah, this F thing is exactly 0 for the XY model.
because you subtract.
Because we've taken T minus T, and XY model is time reversal symmetric in the sense that I've described. Good enough?
Yeah.
Okay, great. Okay, and then I'll just finish my punchline. We have therefore a scaling hypothesis, and so I said we believe that we have this critical exponent or whatever. Okay, sorry, Carolyn, you can go ahead. Yeah, that's Z, I think. Yeah. Z. Oh, let's sorry. What's your question? Beyond relativistic. No, I think this is a non-relativistic theory. That is funny. Yeah, but no, oh well.
Well, we don't know what a field theory is.
No, possibly, yeah.
Is there another question?
Yeah, Grisha, please.
Remind the definition of.
Yeah, no, that's.
Oh, yeah. This thing again, this
You
thing.
might want to put a definition. of that.
Yeah, okay. I'll take.
Yeah, thanks.
Yeah, you're welcome. Okay, let's go. Now we're here. And now we're here.
Okay.
Keep going.
Okay, good. Yeah, right. Okay, good. So I've pretty much finished what I want to get through. So, but I see that I have maybe order 10 minutes left, so I can make a few points. So think of these as appendices if you want, because it's very preliminary. But something that we wanted to do for this model to compare to the nice PRL that I introduced at the beginning of the talk was to study the motion of vortices. So in an XY model, okay, now time is going to the right on this slide, and I'm just showing you 3 snapshots where we start in a totally random state and then relax to some kind of quasi long range order phase. So this is below, I think, the KT transition. And of course, in the XY model, if you wait long enough, you never have any vortices. They interact with the log potential and they annihilate. And in our model, of course, the exact same thing happens because our stationary distribution is exactly the same. Our long time equilibrium distribution function, exactly the same for our model as for XY. So in the rightmost panel for our active model, you also get no vortices. Maybe the only thing to notice is that, I've put the some circles where the vortices are at intermediate times. And we have less in our model. It seems like vortices are annihilating faster. So that's something that we're working on quantifying. Have we modified the interaction potential somehow? So some more numerics are ongoing on this point, but I think it's likely that we have maybe to be romantic, anomalously fast vortex dynamics or some title like this.
Can you start from the right and put two vortices? Because I mean, there are the Coulomb forces and there's like all of this sort of
Yeah.
diffusion.
That's what we're doing. So the numerics that are running on some computer in Colorado right now are vortex, anti-vortex, and then you just watch how long they take. Yeah, that's all we're doing. Yeah. But I don't have plots yet. Sorry about that. Yeah, please, Alan.
There are usually scaling dynamics for the vortices as well.
Mhm.
And a la Hilbert and so on.
Sure.
I'm wondering if you see that for the active, if you see scaling dynamics in your simulation for the XY, but also for the active model, now they.
For the XY model, yeah, we've done all of our due diligence on our simulations. We're confident that they're correct. I haven't seen that scaling precisely. Yeah, so maybe I haven't done all my due diligence. But for the active model, we expect a modification to the exponents or whatever. If that helps, but I don't know if I can say more than that at this point. Was there another question? Okay. So now let me talk again about this PRL that I think quite highly of. So for them, the mechanism of ruining Toner's argument was non-perturbative effects from like these wacky vortices called asters that are actually going to show up and proliferate. And they nucleate and ruin long-range order. For us, we're not seeing them, of course, because we've guaranteed that our stationary distribution is featureless. But what we can do is turn off one of the pieces kind of along the lines of what Grisha was suggesting earlier. So we just do this by hand just to sort of see what happens, check for our model. If we do that, then we'd see actually the exact same qualitative physics. We're doing a much smaller scale simulation here. We'll have better ones when we publish, but we're seeing the exact same physics here. So somehow, and the interesting thing is these VAB mu terms in continuum have 3 gradients. So somehow adding this term that people would usually forget about really qualitatively modifies the long time physics of this model. Maybe it's some kind of anomaly. I don't really know if I have a good answer to what that is, but it may be similar. You know, flows with almost no viscosity are very different from flows with 0 viscosity, right? There are anomalies like this that show up in hydrodynamics. Okay, so now, okay, I still have 4 more minutes left, so I'll give you some, the red means it's even more, this is appendix 2, if you like. But I want to move now and actually try to look at, do a very simple naive renormalization group analysis of this kind of model and compare it to the one that Toner has presented. And in order to do that, it's better to move to the Lagrangian picture rather than talking explicitly about the Fokker-Planck operator like I was doing earlier. This was introduced in many of the talks yesterday, so I won't spend too much time, but one can make a path integral, change Fokker-Planck equation to path integral with the help of an auxiliary field pi. So kind of like in quantum mechanics, the derivatives in the Fokker-Planck equation turn into this pi momentum conjugate field. And your Lagrangian will take this form. And time reversal symmetry, as was explained by Andy yesterday, has a really nice form in this field theory. It's just a shift symmetry on pi, which is easy to implement in a field theory. So this is one reason to work with these kind of theories. So looking at Toner's 2011 paper, he had an equation like this. So here, you don't need to look at the details too much, but V is a full 2-component velocity field. So it has both the orientational degree of freedom and also a longitudinal one. What's going to happen is that depending on the values of A and B in this equation, the longitudinal one, like at long times, is going to kind of go away, and you'll be left with, and that's how this model turns into roughly hours. And if you linearize around an ordered phase and set the scaling of the x derivative just to be what it has to be, he has argued that you get these scaling exponents. Sorry, not that's not the right word. These scaling dimensions, scaling dimensions for maybe engineering dimension for the various operators that you care about. So I'll just leave these up, but yeah, and you can read the paper for details. It's a dynamical RG calculation. For us, this is what our Martin-Sygy-Rose Lagrangian would look like. So here, just to make things a little neater, instead of writing everything in terms of the cos theta, I've introduced this n unit vector, cos theta, sine theta. So this is what our Martin-Sygy-Rose Lagrangian looks like. We can do, from simple calculations, the same kind of analysis, linearize about theta equals 0, and assuming that we're near the xy fixed point, and we find the following scaling dimensions, engineering dimension, whatever. I'm no field theorist, but you get the point. The puzzle from this slide, at least in my view, is that the third derivative corrections that are also ignored by Toner are just as irrelevant, if not more, for us as they are for him. So we really don't expect that they should affect the long distance behavior of the system, but they do. So this is some kind of puzzle. Maybe there's a resolution, because I'm no expert. I'm just going to finish up in 1 sec. So then I'm no expert, but there seems to be something funny. Maybe the naive RG perspective that I've introduced is just not good enough. One has to be more careful, calculate the flow, etc. I'm not sure. I think that's all I wanted to say. So thanks a lot for listening. Yeah, Karen, go ahead. Yeah, okay, let's go right back. Well, this is because yeah, good question. But you're linearizing a state around a state where everything's pointing in the x direction. So the y is kind of like it would be like a Goldstone mode if you really had FSB.
But you're.
Yes. So that must be because we don't have this or something. Like, because the only field that we have is theta. Yeah. So theta can good.
Yeah, maybe this is a related question, but I'm perhaps a bit confused because you were emphasizing throughout the whole talk that your theory is essentially Toner 2, and then now in this field theory, the engineering, the scaling dimensions are so different.
Yeah.
That even at the Lagrangian level, so like what's going on here? Is this just the choice that you made about the fixed point you're expanding around, or is there something more subtle about MSR?
That's a good question.
Can I actually add?
Yeah, please go ahead. Yeah.
Because I think these are all related.
Yeah.
You know, once you do dimension counting and field theories, there's a grinder that we'll go through, right?
Yeah.
So I think one of the questions, I think a related question is that you already mentioned that this is expanding about the oriented phase.
That's true. Which does
So that suggests, so the question I had, which I think resonates with that, is that usually when we write down fixed points that are interesting and gapless, we want to make a list of relevant, marginal, and irrelevant operators.
That's true. Yes.
So for the XY, for the equilibrium XY model, the symmetry breaking field is a relevant operator, and its dimension is changing as a function of where you are in XY phase.
Fair enough. Yeah.
And it remains relevant at the critical point.
That's true.
Right.
Yeah.
So I guess the question is that this suggests, the difference in Y suggests that the relevance of the relevant operator is very different about these two theories. Basically, if there's a predator from this side, is the bug gonna get oriented?
Right.
Run away, just like a magnet would polarize with a.
Yeah. Look, okay, maybe I can.
I'm not sure if these questions are related, but it seems like they are.
I believe they are. I believe they are. So let me say what I can. I mean, I'm no expert, so if anyone wants to talk at the board, and maybe this is probably all we're going to say in our manuscript about this puzzle, and I wouldn't take the dimension counting too seriously by any means. I think if you can take anything from it, it's just to say that it's not crazy that you expect a non-trivial dynamical critical exponent because you have wacky scaling, even at this naive level. But maybe that's the extent to which I want to buy anything on this slide.
Do you see any non-reciprocity?
No, non-reciprocity would be something that we'd have to put in by hand. So that would be interesting. There you would have like blue spins and red spins, and the blue ones want to attack the red. And yeah, so but we could do that too. But I mean, Vincenzo Vitelli's group has studied non-reciprocal flocking in an excellent fashion. So
All right, I think we're actually,
over time.
No.
Oh, great. Okay.
all right, let's thank you.
Thanks.
That was great. Who's next? I don't have a schedule handy. Do I have to call out the next speaker?
I think I just discovered that I'm next.
Oh, okay. That is sooner than later. Okay, are you ready?
I can be.
Sorry.
No, it's okay. Okay.
Charge up or you won't?
No, I just in case, I learned from,
Well, I think it's more important that you get on Zoom. Let me do this.
okay. Let's see, and how do I, is there,
There is, are you on
USB.
what? No, well, no, the idea is that you go on the website, if you don't mind,
oh,
I'll.
please.
So if you go to our website. And you click on calendar, it'll get into the right place, maybe.
Oh, just through the Zoom.
Yeah, the idea is. that,
Oh, okay,
because
I
you're
think
gonna
I
be-
have it, yeah.
Okay, oh gosh. Oh, second, life is just,
Sorry.
no, it's okay. We're not in a hurry. We'll just eat lunch, here. No,
Okay.
and we're good. Okay, very good.
Sorry.
No, we're good. Is Zoom starting? Yes, good. Good. I think the main thing is, yeah. The main thing is that if you go here, right, don't join audio.
Sorry.
No,
Okay, should I leave?
no. The echoes never get, not funny. It's like going to the music board, it's called the curved mirror. Can you share your screen? Yeah, that's the only thing. Okay, do we want to experiment with dimming lights? Is that good? Okay.
Okay.
I think in this audience, you don't have to explain how you say your name.
Okay. Well, just in case. Yeah, let's see. It works. Oh, it does. Okay. So I actually thought that I was speaking in the afternoon. I was planning to make the slides during the break. It didn't quite work out. So I'm a little bit of an outlier here, or maybe a lot. Actually, can like people on Zoom hear me? There's a microphone and yeah, okay. So I will start relatively far away from basically computer science, as it will seem, but then thanks to biology, we'll find our way. And then in the end, we'll realize that everything is physics in the end. And so I hoping towards the end to formulate questions that will reveal me as a physicist. And I hope it will lead to some interactions with you guys because we need a lot of help from physicists. Okay, so these days, you cannot like go to a party or whatever without discussing ChatGPT or some other big AI breakthrough. So let's spend a couple of minutes to look at the technology that is under the hood and underlying this AI revolution. Okay, so under the hood, so it's true that ChatGPT uses a slightly different version of neural networks, and there are some bells and whistles that make it so powerful and interesting, but it doesn't really matter. What's underneath is good old neural networks that are made out of this very simple units that perform weighted summation and nonlinearity. And this secret why these networks are so powerful is because they have this amazing algorithm called error backpropagation, which is basically a differentiation chain rule that allows to adjust the weights on those links in the network based on the errors that the network makes in its predictions. So ChatGPT is self-supervised. This is a supervised version. What that means is that you show a picture, and then the network has to decide whether it's a cat or a dog. And it makes a decision, and then you compare it to the ground truth that was like annotated by humans, for example. And if there is a mistake, that chain differentiation rule tells you how to update the weights of all the synapses in the layers of that network. And after many millions of such presentations, the weights are tuned to the performance that on some tasks exceeds human. So that's the basic idea of this network. But the units were invented 70 years ago. They were put together in this multi-layer network called deep convolutional networks 40 years ago. Okay, so why do we have this revolution now? And I think that the reason is, first of all, the availability of huge data sets for training, thanks to the internet, and the availability of huge computational facilities, and the idea that you can use graphical processing units, GPUs, to train networks instead of CPUs, which gives it more computational power. So that combined produces the magic of which ChatGPT is an example. Okay, so that's great. And this is a truly incredible achievement. And many people could not have predicted even like 10 years ago that this would have happened, but it did. So what's next? Not everything is rosy in the AI land. And here is one example. You might have heard that like a year ago, there was a news story where lawyers used ChatGPT to prepare a brief. And when the judge looked at it, it turned out it cited cases that didn't really exist. They looked plausible, but the network basically hallucinated those cases. Okay. As humans sometimes do, but humans do it in a way that they can be confronted with. Okay, you cannot confront the network. And also you can't understand why it did that. And here's another example on self-driving cars. They make mistakes that a human would not make. And, you can note that most of the successes of self-driving cars are, in California, in this wide roads and nice signs, and try doing this in New York. Anyway, so there are issues. And even if but like if you talk to people in AI, these are really issues that can be solved by some engineering. They're of course working on it, but these are like really small problems. The big problem that AI people want to talk about is called AGI, Artificial General Intelligence. Okay, and they think, I don't, but most of them do, that they can get to AGI by just scaling up existing architectures. Okay, I'm not going to argue with them right now, but just want to point out that even if they were right and they could scale up their networks to achieve the level of human intelligence, their energy consumption grows so fast that soon all of the Earth's energy budget will be devoted to training those big networks. So there is a problem even on that front.
For instance,
Yes.
So training is expensive and hard, but once you've trained it, are we just there to harvest the goodies?
So that's true that most of the cost goes into buying the GPU units that you need for training. And that's not amortized because by the time the training is finished a year later, those units are already out of date. So basically, then there is the energy cost to train them. But even when you use ChatGPT, each query costs, I don't know how much, but there is a cost to each query, which is non-trivial. So
I guess what I was trying to, because we're in such an early stages of, will they train models on for different tasks, and they'll say, okay, we're done burning energy, and now we're going to be like just using it basically, is this curve artificially steep because everybody is rushing to train models or?
Yeah, so okay, so then we have to get into the weeds a little bit. So the current models that are very successful are all language-based, right? And basically they used all the available data already to train them. So there is nothing more coming, basically. There's no data to train on. But if you listen to, say, Jan LeCun, one of the fathers of deep learning, he would say, well, but there is much more data in video sequences, right? So if ChatGPT learned on the, 100,000 years of experience that a person reading 24/7 would get, then for video, I don't think the networks have been trained even on what a 4-year-old has seen. And they're certainly not nearly as smart in terms of understanding the physical world as a 4-year-old. So they think that the next frontier is understanding videos the same way they understand, in quotes, text or language. And that will just, many orders of magnitude bigger demands on training. Does that answer?
Yeah.
Okay. All right. So there is trouble in paradise. But what if I told you that there is an alternative architecture that, at least can be confronted with when it hallucinates, doesn't make non-human-like errors, in terms of energy consumption is under 20 watts, right? And of course, each of you are in the possession of this amazing architecture. But then you would say, well, wait, but what do you mean alternative architecture? Weren't those artificial neural networks inspired based on our understanding of how the brain works? They were. But that was from 40 to 70 years ago. And since then, neuroscience moved ahead, and it is painfully obvious by now that those artificial neural networks have very little resemblance to how the brain does things. And if anything, it's a rather superficial one. So then the proposal and the opportunity that we are pursuing is to actually try to reverse engineer in a little bit more detail what the brain actually does, and hopefully formulate it on the logarithmic level that could allow us to build artificial neural networks which are more human-like. So that's the plan. So now we're going to try to dive in a little bit closer to biology, and then we'll see that physics needs to rescue the day. Okay, so first of all, I want to defend a little bit my claim that the resemblance of artificial neural networks and the brain is artificial, because if you ask the fathers of deep learning like Jan LeCun and Leon Boutou, they say, well, we were inspired by how the human visual system works. We know that there are many layers of processing from the eyes to the decision-making centers, which actually identify an object and decide what to do. And that's why we build this deep networks where each layer works on a higher and higher level of abstraction, and finally making a decision. So that part is actually true, but it's a very incomplete story. And to make it painfully obvious, I want to show you this experimental result. So what this is to dispel, basically what I'm trying to do is dispel the myth that vision is this passive feed-forward process where you just like sit there and the photons are coming in and you just see the world. That's not how vision works, okay? And so here is an experimental proof. This is the tracking of the eye motion of a human subject that is watching the head of Queen Nefertiti here, right? As you can see, the eyes don't stay still. They move all the time, right? And they don't move in a stochastic fashion. They follow certain landmarks, right? Certain parts of the image. And certainly this is an active process. Okay, you can say, well, of course the eye has to move because the resolution of the retina varies and it's only very high, the central 2 degrees of the field of view. So if you want to scan the world with high resolution, you need to do that. Well, that's true, but even And this points in between those movements that biologists call saccades. If you zoom in and measure the eye position very carefully, we'll find out that it's still not still. And there are microsaccades. The eye is constantly doing this. There's constant jitter. And that jitter used to be thought to be stochastic, basically a random walk. Now is thought to be also actively controlled by the brain. So the brain constantly scans the world with the movement of the eyes in a dynamical, active fashion. Question. Oh, okay, a very good question. So in this case, there was this gruesome mechanical device that actually, touches the contact lens on your eye and tracks it this way. Nowadays, most of the tracking in human is optical. There is an infrared camera watching the eye. In animals, they implant a metal coil, induction coil, and put the animal in the magnetic field, and that's the gold standard. Anyway, so now we can track very well, but the reason I put it up here is to convince you that these are not artifacts, okay, that these are necessary parts of perception of these movements, because if you're using this device, which is basically like a negative feedback loop, to stabilize the retinal image so that, the eye keeps moving, but like the image on the retina does not move, so it's still, then the image goes away. Okay, so the subject basically goes blind in a few seconds. So that is to dispel all the ideas, well, the brain would like to keep the eyes still, but it can't or it shouldn't. No, those movements are essential, central components of the visual perception process. So vision is not just a feed-forward, passive feed-forward process, it's dynamic. And also there is a closed loop because the motion is controlled by the muscles based on what the eye sees.
How do you mean the image goes away?
Just, it goes blank. It's just like,
How do you see it?
it's just all white or all gray.
That's self-reporting.
Oh, yeah, but you can ask them, like, what do you see? And
So this mechanical thing is it like prisoners or? This seems like a permanent,
that's how you used to do the things in
Okay,
the
that's
60s.
cute.
That's a standard, yeah. Yeah, these days, this is very painless. You just have a, infrared.
the idea of arresting the eyeball.
No, it's not, yes, you can paralyze that, but then that's crazy, right? The eyeball keeps moving, but its movement is sensed by this lever, transmitted mechanically to the movement of the slide in this case. And then the slide is moved to
Oh, I
compensate
see,
for
I
the
see.
movement of that.
You try to
Sorry.
move, but it moves.
Right, so you think you're moving your eye.
No, I thought you were just nailing.
No, that, yeah, you can paralyze, yeah. Okay.
Okay, all right.
Okay, so it's completely necessary. And so then the view of what the brain does is not this feed-forward network that responds to a picture presented at a given time, but first of all, the temporal dynamics is important, right? So it is the changing in the correlations, temporal correlations in the input that the brain is processing. So there's temporal dynamics that is crucial. And then there is a feedback loop here, right? That is also important. So it's not a feed-forward process. Now, it is true that there are other artificial neural network architectures that try to put in this behavioral loop, like reinforcement learning, for example. That's why I said loops. And the reason is that if you actually zoom into the brain, this is not the only loop. And if you look at the network of neurons inside the brain, okay, that is called the connectome, this is this little worm which has 300 neurons, and we know all the neurons and all the connections between them. So we can plot it as a graph, which generally processes information from the sensory inputs to motor outputs. But if you look very carefully, it turns out that 80% of neurons belong to loops. So this is a loopy graph, not a feed-forward graph, not a tree. Loops upon loops upon loops everywhere.
So in the beginning, you said that like the artificial neural networks were powerful because they have this backward pass thing,
Yes.
but that's not a feedback loop?
Exactly. So thanks for that question. So what I'm going to tell you, okay, I have to jump forward. Okay, so that the units, the basic units that were invented 80 years ago, right? That do weighted summation and nonlinearity did not have a feedback loop and did not have the dynamics. But the history of neural networks, artificial neural networks, can be viewed as trying to compensate for this rudimentary and flawed design of the basic unit by putting in other things. So to put in the big loop, they designed the error back propagation algorithm. To put in the dynamics, they have another trick called RNNs, or short-term memory networks. The names are
So if I think of it as a graph, what you're saying is the engineered sort of a circuits have only long loops, like a random regular graph where it's
Exactly.
basically like a beta lattice with just
Exactly.
big loops, whereas the actual network is a dense
Exactly.
connected.
Exactly. And most importantly, if you think of each neuron as a part of a loop, which is what we are proposing, right? A dynamical system that is part of a loop, then it can use its input as a teaching signal regarding its outputs, because its outputs affect its environment, which are other neurons in the world, and then it can monitor the effect of its environment, use it for learning. So that's the crucial difference that was absent here.
That would be shallow learning,
Right,
not a deep learning.
exactly, exactly. That's the point. I think there were, yeah.
So in the second model, there has to be some kind of time component, I guess, because if the dynamics are just feeding back on itself, could it be, and it's all happening at the same time, couldn't you just essentially make the blob bigger and collapse the
So I think that what I'm going to tell you is that we're going to choose a level of abstraction of each neuron. I'm going to argue being a feedback controller. But there is nothing special about that level, other than we have a lot of experimental data that we can test our theory on. I believe that if you take a group of neurons, you can think of all of them as a controller, and you can coarse grain all the way to the whole brain, and view the whole brain as a controller. You can also go down below the neuron, because there are these things, the connections between neurons called synapses, and I think that each synapse is also a controller. So there is this big problem that was going to be my question number 2 to you, is how to put together those little elementary controller units that are feedback loops into a big thing. So some kind of coarse graining that we don't know how to do.
Active idling.
Exactly. Okay, was there another question?
Yeah, so the distinction with something like a recurrent neural network is that that's still layers, you still only sort of feedback to the previous layer as opposed to
The distinction is how you train it, because even though the networks are, well, depends which one you're considering, but even though the network has this big loop maybe, okay, or has temporal components, the training is still use error back propagation, which is it's hard, an algorithm for feed-forward computation, right? And it doesn't take into account the loops, because once we have a loop like this and we have this dynamical systems, then the proper framework to analyze this is using control theory, which is basically a field that was designed to handle loops and dynamics. So that's what's missing in the current artificial neural networks. There's no control theory there. Okay, any more questions? All right, okay, so that's what we are proposing. Surprisingly, this is actually a novel proposal that each neuron acts as a feedback controller, even though for the brain as a whole, this has been argued many times before, and even big parts of the brain, like the ones that move the eyes, were viewed as a controller. There's some classical work there, but no one dared to suggest that a neuron could be a controller. And why is that? And we think that's because a control is a computationally intensive proposition, and a neuron is a very simplistic biological device, relatively speaking. Okay, and to make this more concrete, we are going to think of the environment as being a linear dynamical system, in this case, discrete time, but it all doesn't matter. And, you know, there is a autonomous evolution, x equals ax, and then you control it with u and, you know, usual things. So the reason it's computationally difficult to control for this kind of environment with some control law is, first of all, in biology, there's no way for a neuron to know the dynamical parameters of the environment, right? There's no way that it knows ABC because ABC may not even be the same from second to second, okay? So the first step, if you want to control a system like this, is to actually infer ABC by collecting a lot of data, which are pairs of U and Y. And from there, there are existing methods called systems identification that allow you to infer A, B, and C. Okay, so that's the first step. The second step is knowing A, B, and C, you compute optimal K, which minimizes, say, quadratic loss in U and Y. Okay, and then that is also known how to do, at least for linear systems and quadratic losses. There is a closed form solution. But the problem, just like with systems ID, these are pretty complicated mathematical expressions involving matrix multiplications, inversions, and so on. So there's nothing that a neuron, I mean, it's hard to think of a neuron to even represent those parameters A, B, and C, let alone compute them through systems identification, compute optimal control. So is hard, and also if the system is partially observed, that means that the dimensionality of Y is less than the dimensionality of X, then you cannot control in terms of Y because it's not a state variable, right? You need to infer the state in dynamical system sense to control, and that's X hat, okay? So that's the third step, also known how to do, but again, computational tricky.
That U influence of environment is kind of active inference action, so this how
Yeah.
you actually see the channel, etc.
Yeah.
So this is U, your active influence.
Yeah. Yeah, so it's any kind of influence on the environment. So for a neuron, it would be like its output spike and whatever. Okay. Okay. So why am I telling you about this? Well, because 25 years ago, there was this development in control theory that is a game changer. And it is called direct data-driven control. And what it basically is a realization that you don't need this intermediate step of representing A, B, and C explicitly. Instead, you can map the observations Y to the control signals U directly. And you can learn this map based on the previous pairings of Y and U, because you have to learn online. So there are previous experiences, like remember, like learning to play tennis. This is, every time you hit, you maybe not perfect, but you learn a little bit about the system and learn how to control it. And so this kind of training is what allows you to learn the direct mapping implicitly using the dynamical systems model, but never representing it explicitly.
So the usual common filtering story is under traditional control? Is that?
That's right. So usual control, most of the textbooks say, given A, B, and C, what's the optimal K? Okay, Kalman is when there is also a noise term, and then K has to filter out the noise. Okay, but basically everything is given, even the variance of the noise.
Sorry, I'm just getting confused. So the Y is the input into the neuron.
Yeah.
And what is the X?
So X is the latent state of the system that you don't see, right? So like, for example, Lawrence, right? It is a three-dimensional model, so X is three-dimensional, but you may be observing only one dimension. And so you see this time series, and that's Y.
But
Okay.
the output of the neuron doesn't, in that picture, it doesn't look like it depends on Y.
It depends on Y through X hat, because to reconstruct X hat, you need Y, right? But if this is partial observed, then you need time delay embedding. You need recent history of Ys to reconstruct X hat. Okay. All right. So that's basically what we did. We said, okay, if we use this data-driven control, we can actually map this calculation to what a neuron does. And it's plausible to imagine that the neuron with its pretty limited capabilities can actually perform control. Okay, so I'll just spend a couple of minutes to go through the mechanics of how it's actually done. So it's actually very, very simple. It's simpler than traditional control. So if you haven't studied traditional control, you can just it's a relief, right? Because then instead of studying all that, you just have to learn the data-driven control. And it's very, very simple.
Yeah, sorry to, just before you go on, I don't know really anything about machine learning, but this looks a lot like maybe numerical solution to differential equations.
Yeah, I mean, you need to integrate, yeah.
Yeah, so I mean, for that, there are lots of, I could imagine more complicated schemes. When you create it, right? Like this looks like a kind of forward.
It's control, it's U, it has U, which is, it's not solving the differential equation, you always add U. As a product of it's really control, you have some function which you try to.
So let's do a specific example that maybe help. So the simplest possible dynamics is when X is a scalar, okay?
Yeah.
And in discrete time, it gets adjusted by AX,
Yeah.
where A is greater than 1. So say A is 2, so you start with X equals 1, then it's 2, then it's 4, then it's 8, and so on.
Yeah.
Okay, this is unstable, it's going to diverge. Okay, the loop has to control itself so it shouldn't blow up. So we want to come up with a control signal that will suppress this instability by subtracting just the appropriate amount so that X goes to 0. And that is based on this U that is computed from X. In this case, it's fully observed. There's no Y because it's just like CX itself by just scaling X by W, and that's your output. So the question is, what's the appropriate W to send xt plus 1 to 0 for any xt? And for a system this simple, we can actually do it in one step. Okay, just plug this Wx into this equation. Okay, and if I require that for any xt plus 1 has to be 0, that means this bracket is 0. That means W is minus A over V. This is like week 1 homework problem in Control 101. But the neuron cannot do that. Even that is not available to a neuron because the neuron doesn't know A and B. So that's where direct data-driven control comes to the rescue, okay? And then we have to think in a completely different way that I will try to explain first geometrically, then algebraically, and hopefully, you'll find it actually appealing. So geometrically, the way to think about it is the following. So there are 3 numbers, xt plus 1, and ut, can be thought of as components of a 3-dimensional vector. Hence, it's a 3-dimensional space. But because of this dynamical equation, the legit triplets don't span the whole space. They only live in this 2-dimensional, in this case, subspace, which is this blue plane, because of this constraint. The slope of the plane is dependent on A and B implicitly, right? So all the legit vectors, like these blue vectors, that are previous triplets of xt plus 1, and ut, they live in this blue plane. Then we know that for any future xt, this triplet has to also live in this plane. And if our goal is to find ut so that xt plus 1 equals 0, means that that vector has to be this red one, which lives in the xt plus 1 equals 0 plane and the blue plane, okay? So it's in the intersection. So once you have that intersection, you take your xt, you set up the orthogonal line, and then you project, and that's your ut. That's the control that will set xt plus 1 to 0. That's it. Okay, so it is really all that simple as I'm showing you. Okay, algebraically, it's called the fundamental lemma. It basically tells you that any triplet is a linear superposition of previously seen triplets. Okay, so these are the ones that span the blue plane, and these are the new one that you want to set to satisfy your desideratum, which is xt plus 1 equals 0, for example. xt is measured, ut is what you want to find out. So you have to solve these equations, and then they have this coefficients g that you don't know. So, okay, sorry. So what you do, you solve the first two equations for g, and then you plug in g in here. So that's the basic idea. The reason it's called the fundamental lemma is because this isn't really always true. And you, of course, know that the necessary condition and sufficient is that these vectors have to fully span the subspace. So, for example, they cannot be linearly dependent on each other because, so for example, if all the blue vectors point in one direction, then the orientation of the blue plane is not determined. It will flop like, a weather vane in the wind. And so you don't know where the intersection is, and you can come up with a control. That's the Achilles heel of this method, which combines systems idea and control. So whenever anything is constant, for example, if we found the optimal W minus A over B from this algorithm, and we fix that W, we are in trouble. Because once it's fixed, yes, it can control for this A and B, but if A and B start to change, the system will not be able to adapt. And so the way to solve it in this case is to add noise to the control. If the noise is little, small amplitude, then the control is still close to optimal. But then we get this exploration which spans the subspace and allows you to maintain adaptability. And actually, it turns out that the brain is full of the noise. And in many cases, people have shown that it's both intentionally generated and necessary for learning. So this kind of like seems that this method reproduces a bug. So let me finish the sort of the plan of computing optimal control. So we want xt plus 1 to be 0. Xt is the current measurement. And then we have this history of those guys, and we are solving this for u. And then there is a big question that you may want to ask me now, which is, wait. But the whole reason you build this data-driven control framework is because you said neuron is not that computationally powerful. And so how is it going to do this, right? Is it going to store all the past triplets, all the past trajectories that it has seen? And then at every time step to compute a new set of coefficients, G? This is just crazy, right? Well, thankfully, the neuron doesn't have to do it because we can do the algebra, we can compute this linear regression by pseudo-inverse, plug it in, and then it turns out that the control law W depends on just covariances like this ones, which are basically like in this case, this is a number, this is a number, and so a neuron can store two scalar numbers. It's capable of this. And then all it has to do is just to update them online as the time goes on. Whenever there is a correlation between the X, which is like the, say, the spiking of the presynaptic neuron, and U, the spiking of the postsynaptic neuron, when one follows the other, you update this sum. And when the reverse order happens, that this spikes and then this spikes, then you update this sum, and then the synaptic weight is the difference of the two sums. That's just like a result of algebraically solving those equations. And this updating rule is something a neuron can easily do. Moreover, there is experimental evidence that it actually does. So this is like I'm not going to go into details because it takes a while to explain what this is, but people have measured how synaptic weight changes as a function of activity of the two neurons, the pre and postsynaptic, and it turned out that this part can be viewed as an instantiation of the first term, the green part is the first term, and the blue part is the second term. So it actually does correspond to biological reality, but not to the artificial neural networks. This has nothing to do with artificial neural networks. So that's the learning rule that can potentially replace error backpropagation.
Like from approximation. So what is the
Okay. So this is actually, this is exact. What I dropped, the reason there is an approximation here is because there is a denominator that depends on covariances of X, self-covariances. That's all. But I dropped it because it doesn't depend on cross covariances, which is what the learning depends on. But otherwise, it's exact. There is no No,
Is this beta is like a Lagrangian multiplier?
yeah, beta is the cosine of the angle between the first row and the second row, which comes out when you do pseudo inverse. Right. So it's less than 1 generically. Any other?
These adaptations and learning, they happen in synaptic connections or elsewhere?
So this is just one synapse. Yes, that's what happens with one synapse.
So this belief that it's all in there. or-
Exactly. So that's why backpropagation, the artificial neural networks use, is biologically plausible, because it requires a synaptic update of a synaptic weight in that case, requires the knowledge of the error that the whole network achieved on telling you if it's a cat or a dog. And the poor synapse in the brain cannot possibly know about that, because it's like less than 1 micron in size, and it's packed with gazillions other synapses like this, and you can't communicate information. Of course, the backpropagation algorithm is run in software and the CPU architecture, so there's no problem in communicating variables. That's why these two things are completely algorithmically different.
Just, yeah.
Okay.
Go.
And can you actually construct in a network from that actually learns something bigger? That's the problem.
Right, so that's what we need to do. We haven't done it, and I'm asking for your help in figuring that out.
So, as being a novice in this, as I understand, like the old story for these synapses was that there's this very nonlinear 0 to 1 activation, but in this kind of linear theory, can you build that? Is that important for the story? Do you need to
Right.
build that in somehow?
Right, so that's a good question. So this model is fully linear. The reason we don't need a nonlinearity because there is a control loop, there's a
Right.
feedback loop, so things are fine. Okay, now we know that actually in biology, each neuron, or the dynamics is of course nonlinear, and the controller is nonlinear because it spikes. So we haven't solved that problem yet.
Is it related to analog versus digital? So in a sense, you're analog
It-
here, right?
Yeah, so it could be a mechanism of error correction, this saturation sigmoid. But I think it also has a computational meaning, but we should discuss this offline because that's a whole other tangent. Okay,
All right, it seems to me that so far what you have is through this control as a self-stabilizing.
exactly.
But then if you look at and this experiment is designed to sort of probe that self-stabilization, but this model, as you already said, doesn't have spikes, doesn't have, so the question is that before you start
Right.
building the network,
Exactly.
can you just understand the mathematical necessities to have
Exactly.
a single?
Exactly. So that's actually a question. I forgot to put it on the slide, but this is question 0, right? Is to get this result, all we had to assume that there is this linear dynamics closed loop, and that our goal is stability, which is sending X to 0. That cannot possibly be a goal for every neuron, because if every neuron had its goal, then it's easily solved by just silencing the whole brain and just dying.
It's a stable equilibrium.
Stable equilibrium, okay? So that's it. So that cannot be, this is the necessary condition. Of course, you can have a loop without stability, but this is not sufficient. There are other objectives that need to be met for this thing to work, okay? And we don't know what they are. We have some ideas now, but that's kind of like open for discussion. And you need to know, as Vadim said, to know what those objectives are before you start putting those units into a network.
But it seems like what Aaron just reminded us, that the switching behavior is like what a neuron does when you're trying to switch. Do you have other fixed, right?
Yes.
To have switching, you have to
Yes.
have other fixed.
Exactly. So it does, of course, and there is a lot of like switching in the brain. You can see it all the time. But again, like then we have to say, what is the objective of that switching?
But is switching as a single neuron phenomenon?
That's a good question. So that is actually not very clear. There is evidence for both that as a network effect and the single neurons. So there's probably both. And the way we are kind of trying to think about it is, at least myself, I like to think about those nonlinear processes as kind of like trying to learn the nonlinear dynamical system. Like think of some kind of like heteroclinic orbit and, you know, going between different hyperbolic, settle fixed points. And the neuron would be switching when the transition from one critical point to another happens. That would be kind of like a neuron as a detector of criticality. So that's kind of like my pet hypothesis, but you know, there are other possibilities too. Okay. So let's see. So yeah, so that is not very interesting for you, but is to say that, you know, we're not just like proposing this theory, but it actually does map to a lot of neuroscience experimental data that previously seemed completely unrelated, but now come out of the same theory. And that's good, but that's probably you don't care about. Okay, so now in the remaining like 2 minutes, questions for you. So as already came up, the real neuron is not an like graded potential, whatever, they're not an analog device, it's more like a digital device. So it gets input, which is here provided by an experimentalist to make sure they know what it is. So the current over time looks like this, okay? And the neuron's output is this very short, less than a millisecond long spikes, they're called, which are basically like the solitons that travel down the axon. And so they are noise resistant, they're certainly true, but that may not be the only thing about them. And the reason I put this diagram is their amazing precision, temporal precision, so that, you know, every time an experimentalist injected this current waveform, they got exactly the same sequence of spikes down to a millisecond. What those spikes symbolize in algorithmic terms, we do not know. There are various models, but we really, really don't know. So one standard way to think about them is to analyze the average current waveform that precedes a spike, and it usually has this, you know, biphasic or multiphasic form, which detects the rise in the current. There's some kind of increasing input that the neuron usually signals. If you think of a neuron of a controller, there is an increase in input, that's probably an instability. So this is the exponential divergence that that neuron will compensate by providing a spike. Okay, so think of a spike as like odds chaos control or something like the surgical control that that compensates for instability by pushing against it, by detecting exponential. So we're trying to analyze experimental data to show that there is evidence for this. And you know, if you look at Lyapunov finite time Lyapunov exponents, indeed they pick up before the spike. So it does seem like we are finding that there is some signature of instability and the neuron responds to it. But that's still like unclear, you know, how the neuron does it, what exactly the mathematical algorithm is being solved here. Another interesting aspect in that, like I should probably mention, is that, remember I said like 80% of neurons are in a loop. What about the other 20%, right? They're still feed forward, right? So, you know, you can't think of the neurons in your retina as controlling much. I mean, it doesn't help. I mean, of course, you need vision to control your actions, but a single neuron producing a spike, you know, how can you think about it as a controller? It turns out that you don't need to. All you have to think is that there is a controller somewhere downstream. And then it turns out that there is something called data rate theorem in control theory, which says that if you want to control an unstable system, your information capacity has to be in knots, has to be equal to at least the top eigenvalue of the dynamical system. Otherwise, you lose observability. And that has to do, of course, with entropy production, right? If there's an unstable system, it produces entropy. And if you don't track it fast enough, which is this information rate, then you lose observability. So you can think of spiking a neuron as reporting that there has been enough exponential divergence, enough entropy production to signal downstream to make sure that the control is possible. So this controller view is like useful, but it doesn't require that every neuron is a controller. All you have to allow is instabilities. So the key is to allow instabilities. Okay, and the question 2 is how do you put together those units into network? Because each neuron thinks it's a controller of the environment, but environment is made out of neurons just like that one. So each of them thinks it's a controller. How can you put them all together? That has to do with the correct objective function, which we don't know. And then all together, they have to coherently produce some behavior that actually does something useful. So there must be like some multi-scale coarse grain in hierarchical processing happening here. And okay, I don't know. I always hesitate to do this, but like this is so tempting that I should do this. And
turn off the video.
yeah, turn off like off the record,
Turn
off the record. Okay, so there is evidence.
Excuse me?
No,
If
no,
you're
I'm kidding,
serious.
I'm
Oh, you're
kidding.
kidding. Okay.
There is evidence that the activity in the brain is close to criticality, right? So there is this, if you track the propagation of activity in terms of avalanches, you plot the distribution of sizes and the time constants. They're all power laws that are related to each other. So there is evidence that there is criticality there in terms of that activity propagation, okay? And some people think that that has something to do with consciousness. Okay, so that's the part. Good to say off the record, okay? Because what is consciousness is our ability to like perceive everything about us, right? Like you can think about how is my toe on the right foot doing, okay? So I have access to everything, but the network is 100 billion neurons large. How can I have access to everything? Well, you have criticality, you have divergent time scale, spatial scales, then maybe you can do that. So that's the connection with consciousness. But now the really interesting part is that if you measure that criticality as a with time, how it changes during the day, that when you wake up in the morning, the system is very close to criticality.
In what terms? How you measure it?
So these are the
Information, what quantity?
so these are the distribution of avalanche sizes and time power laws, and the critical exponents between those power laws. As the day progresses, you deviate from that, and when you go to sleep, the avalanches are pretty subcritical. So the theory is that, hypothesis is that the sleep is necessary to restore criticality, okay? So that the next day you wake up and the system is tuned back to critical. Why is criticality violated? Because of the external input, right? So the idea is that in sleep, you turn off the external input and you somehow propagate activity within the network and you reestablish criticality. But the external input that you get through the day, this bad news that you hear all the time, that disrupts criticality.
Makes us unconscious.
Yes.
So just like on this experiment, they do it when people are sleeping and dreaming as well.
Yeah, so they also measured this exponents when they dream, and there's different between different stages of dream. I'm not an expert, but I can give you the
So
reference.
This is published, this sort of attenuation of criticality versus
Yes.
email traffic.
Yes.
Is existing.
Yeah.
Have people tried to do controlled experiments? Is there LSD-induced criticality?
Okay, I'm not an expert on sleep, but there is this connection. Anyway, sorry I took so much time, but I want to thank the people who were instrumental in getting this work written up and done and written up, and it's getting published. In the meanwhile, you can get it on the archive, and Josh is here in the audience. Thank you.
Well, if there is a burning question that cannot be asked over lunch, please ask it. Otherwise, let's adjourn.
When we reconvene?
2 o'clock, I think we.
I'll leave Zoom.
Huh?
I'll leave Zoom.
Yeah, no, you're done. You earned your lunch. Oh, wait, no, I don't want to.
Oh,
Sorry.
You want to tell people on Zoom when we?
We're reconvening at 2 o'clock. You mean more?
Yeah.
Okay. All right, we resume with Pavlovetsky. You need stick.
This is what we used to use when we talked.
I know, I remember this one. So,
I went to a school when I was
I think
fifth
you were-
grade where they actually did have some corporal punishment.
So I actually had a physics teacher who had a 10-foot pole. who would-
Yeah,
so-
right, yeah.
I know, I did.
So, excuses for any errors and stupid looking things today. Last Sunday night when I was preparing my talk, all of the stuff of entering equations, that the apps were broken for some reason. So what I do is I copy equations with a image and I put it in my things. Well, let me show you what happened. This is what came when I had let me see if I can put it here. Yeah, that's okay. Can you see this? So can I move it? Yeah, okay, should be able to move it like this. Well, it's hard to see. Maybe I'll pull it down like this. So you can see, for example, this one down here is this guy up there. It's all different. And my wife sent me an email telling me that a front page article in the Times said that Windows has changed its fonts just a little bit.
Yeah.
And after doing that, puff. So, this is the hard work of a theoretical physicist. Anyhow, I'm supposed to talk about chiral systems that exhibit odd viscosity and other things. And I'm supposed to send you to a theory that we have set up, which actually is really quite nice. So what my goals are going to be, first, we're going to talk about dynamical properties of rotational active liquids. What is chirality? And a demonstration of one of its components. I actually have a demonstration I'm going to show you here. And then we're going to define some variables and show that there are two ways from going from a microscopic theory, which is the one where you write down the energies in terms of the atomic motions, and show that there are two ways you can do it, one of which is not correct. And I'll discuss the elementary excitations. There's one that has only odd viscosity, which is the incorrect one, and the other is non-reciprocal with excitations of the model. And then the question of what hydrodynamics is not really given a precise definition anywhere I've seen, but you usually hear that when you have hydrodynamics, you want a theory which takes care of coarse-grained gross variables, and your theory of equations and motions and so forth should stop at second order in the gradients, and that's it. So what we'll do is set up a theory which starts with the microscopic and goes to the macroscopic, and then using Poisson brackets and things like that, we can actually get the equations of motion, which for this apparently harmonic theory gives us almost all of the properties that you expect for a system that has chiral symmetry. And then I will look at, so that's one part of what hydrodynamics is, namely that it's the long wavelength limit. The other part is that you ignore the high frequency modes because they decay quickly into something that's determined by the low frequency modes. So all three of those things, or two of them, whatever it is, you can see in this model. So I hope I get to that. So we'll start with saying, chirality is an important part of this talk. And I have here an example of what a chiral object is and how it can do strange things. So here is a boat with two passengers, the turtles. If I go like this, it's not chiral. If I turn them like this, it's also not chiral. But if I do this, like that, right? Now, suppose I had the theory at the other end, it would be like this, and there's nothing I can do to have this guy superimposed on that guy. And that's what chirality is, according to, which one was it? Remind me of the.
Kelvin,
Huh?
Kelvin.
No, it wasn't. It was, I forget now, one of the French of about 1860 or something like that. He was, yeah, anyhow, so, and this is just to show you that chirality can influence dynamics. So here we are in a, I don't know if you can see it very well or not. Here we are in a, in a non-chiral state. It's happy spinning around like that. Or we can spin it the other way. It's just as happy. So that's the non-chiral state, and it behaves like a non-chiral state. Now, let us do this. So this is a chiral state. And when I spin it that way, it wobbles a little bit, but it's happy, right? It keeps on going. Now let's try it the other way. No, I don't want to go in that direction.
Oh, it goes back.
Now it's not happy,
Yeah. So this is actually, oddly enough, this is called a Ukrainian rattleback. Because I actually ordered it from an outfit in London who had commerce with the Ukraine. So, and I should say, the next picture, now I'm going to be going back and forth between I have a copy of a seminar that my collaborator, Tomer Markovich, and he shows here, where is it? Oh yeah, this is what we want. So here are his examples of chiral active matter. And the one I just discussed was the one in the middle here. What I did when, I should tell you the story of how I figured this out. We had a talk at Penn by some guy from Japan who studied this kind of things. And so he showed us this, and he spun it, and he showed the back end. And when I saw this, I knew it was talking about chirality. So Jerry Golub and I got together a undergraduate who took paper clips and converted the paper clips into what you see here. So the one in the middle is achiral. The other two are of opposite chirality. And sure enough, if you put it in one of these shaking beds, I used to have a movie of this, but they've changed the format, so I could. The thing, anyhow, we made a gas of them, right? And that's what you see here. So the spinning induced by the wiggling of the individual molecules, quote, induced motion, and the motion then coupled with the motion of the whole thing, then you can see the whole system rotating around. The only thing that was a little odd about that is that the theory to get the right answer required a very large penetration depth. We're used to saying that the boundary condition of a fluid with a solid surface is just on the line or on the surface of the boundary, but you could have depending upon the parameters in the problem, you could have the effects of the surface penetrating further into the bulk.
Like sleeping glimpse.
Yeah. So, something like that. You're right. Yeah. Most of these other things are biological, but certainly, there's are really lots of different shape objects and so forth that you can do. Is that a question back there?
The rattleback
Yes.
can actually reverse many times. It spends more time going in one direction.
Well, no, but if I put it, if it has a force on it, I mean, if I put it on a vibrating table,
Yeah.
then it has a constant source of energy. And they always turn in the same direction.
But they reverse.
No.
No, they don't.
Yeah, they do. They reverse. and
No, they do it if I
It goes the opposite
if I
way.
do like this, it turns around and it reverses.
And it'll continue and then
But-
reverse
but-
again.
Well, what happens in the vibrating table is they just keep on going because they have constant, energy coming from the bottom.
Okay, that was my question. There is an example of a rattleback that will reverse several times.
Yeah.
And I was wondering if in the vibrating table case, the stables.
Okay, so this was an experiment carried on at the mercy of this undergraduate and had to twist. He did 700 of them. Anyhow.
So, but it seems like the rattlebacks that reverse multiple times are not, that are somehow not this one.
Yeah, you need the random,
Yeah,
other random.
it's not
elements.
unique. I don't think.
No, it's just that sort of coincidence of friction that you don't see the reverse. But if you make one, a large one out of glass. you
And,
get-
and how are you driving it?
No, it'll just keep on reversing.
Well, but there's friction in the base that slows it down and stops it unless it's removed.
I think what he wants is the friction that's weak enough that it.
Yeah, if the friction is weak enough, there's two modes. There's a vibrational mode that favors rotating one way.
Yeah.
And a different mode, lateral mode.
Yeah.
Favors rotating this way. And so in fact, if you have enough energy to start with, you'll spend most of the time going clockwise, but a little bit of time going.
Okay, we didn't, I don't recall that we looked that closely, but what we did see was all of them spinning essentially in all of them in the same direction at the time. I'm sorry, I don't have, I actually have the sibling of him, but somebody stole the nose. Okay, anyhow, that shows that you can do mechanical experiments with odd viscosity, well, with chiral systems. Okay, now let's see, what am I supposed to do here? Okay, so a couple of things we want to know to start with, that we have a linear irreversible thermodynamics. You know, the rate of entropy production is, yeah, okay, we can do this. You have a current and a force, and the product of those two things gives the amount of work the system's doing, and it changes the entropy of the system. So if J has the form of a second rank tensor multiplying the force, there is the symmetric part, symmetric under interchange of I and J, and the antisymmetric part under interchange of I and J. And if you look at the total entropy produced, the part with the even D, the Dij is equal to Dji, actually does work. But the odd one, the odd under reversal of I and J actually has Rij as minus Rji. And since Fi and Fj are the same field, the Frij Fj term vanishes because of the symmetry. So that means that when you have a system like this, the odd term, that one does not contribute. And that means that that's part of a perfectly non-dissipative system, unless I add the dissipation by hand. Okay, so this is, you know, a real experimental realization of this is that you have something in an external magnetic field, and then Dij is proportional to minus Dji with a minus B in it. And that fits in nicely with this morning's talk, because it shows that under the magnetization system, you actually have, it's odd under direction reversal, and it's odd under time reversal. So you have one of these things where it is, what is it? RT, I guess is what you call it. Okay. So actually, because of my problems getting equations in, I am going along with my colleague's original presentation, which is close enough to my own that it doesn't matter too much what we do. Okay, so the odd viscosity we want to talk about is you have, normally we think of viscosity as being dissipative. And so the eta ij there, eta ijkl is, it's part of the model that doesn't have any dissipation. So eta ijkl under odd viscosity is odd under ij and kl interchange and become kl and ij. So having this system, which already incorporates derivatives with respect to the speed or the velocity in the system, is the odd viscosity by itself. Now, when you look at the theorems in you know, the history of the odd viscosity, it always is this form of the, here's the form, this eta naught right here, has epsilon ij k's in them and delta ij's are the same. So this is what we heard this morning, is that you can have coupling between the compressional, isotropic compression and the shear modes of the system. So this was, if you look, ask what happens if I add a magnetic field, what happens if I've rotated a system, all of those things really looked only for this form. And here is the form that our colleagues at Chicago used for describing what the various viscosities are. So this one is, you have the compression, the rotation, compression like this, shearing like this, and shearing like that. And those four things get mixed up into making the eta IJKL have, well, at maximum 16 different numbers, but it's easier than that. Okay. Now, what is the origin of the chiral activity? Well, if you can create something that has spinning objects in it, say, for example, vibrating the table with these, then you want an equation for what the angular momentum density is. Oops. We're down to this one. Yeah. And so this is the equation for L. And it has these terms that are basically have gradient-like things in them because they are, well, we'll see in a minute what that is. So what we want is, this is stuff that was not my field, so I'm skipping it. Okay, so we want to be able to see in the motion of the system what the active components are. So we're going to take a model now where we have a system of particles, which I'll call molecules, where we have two atoms that are connected by a rigid rod. Now, the advantage of that, I mean, the reason for doing that is we certainly want an object that will spin and know how to deal with it. Now, we could have just taken a sphere and said, we're going to let the sphere spin, and we would have both the rotational degrees of freedom and the translational ones. But it's easier to think about it as being a dumbbell like this with a rigid rod between them. Now, so what this does, the rigid rod reduces the number of degrees of freedom that you have. The two balls alone each have d translational degrees of freedom, and well, think of them as being point sources. So they have three degrees or d degrees of freedom, both of them. The two together then have 6 degrees of freedom. But if you put this rigid rod in the middle, you've reduced the number of degrees of freedom down from 6 to 5. There are 3 translational modes and 2 rotational modes because the thing can only move perpendicular to its sphere. And so what we want to do is to make sure that our expression for the total momentum in the system in hydrodynamic theory, which we've already discussed, stops at a certain order in the gradient as you expand it. And in this case, it's fine. You get all you want by going to first order in the gradient because it has a length scale and a grad here, and we'll find that well, we'll see in a moment what this does. So the important thing is that this form, written like this, actually has the property that the integral over the whole volume of R cross G is in fact equal to R cross GC. So that's the center of mass. The GC here stands for center of mass. And then it has L, the angular momentum density of the spinning. And you can see that this in fact has the total of the displacement rotation, that is the rotation of the individual molecules, and it has the rotation of the molecules themselves. So that you have this, that's the first part, and this is the second part. So you really do now have a system that, in the absence of external forces, conserves angular momentum as well as momentum. And there's a long-going controversy sort of about what happens when you add G. And there's a famous article by Martin and a crew in France saying that, well, you can write it that way if you want, but I know how to tell you that I can convert this cross L from a single odd tensor to a sum of 3 different fourth rank tensors. But such that altogether, what happens is the curl L or the L term itself, or the curl L term, I should say, becomes symmetric. Now, that leads you to the impression that, well, let's not worry about the angular momentum, the spin angular momentum, because we know that the physics is only going to be only in the stress tensor itself, and invariably people throw that term away. But we can't do that here because we're driving the spins with external forces. So the statement that you don't have to worry about L in a system that has chiral objects, but where total angular momentum is conserved, they're right. You basically can ignore L in that sense. But L itself, the little L itself now has its own equation of motion, and it involves having an external torque, and its behavior is really determined by the external torque, which you don't see in the other one. So we don't have to do any apologies about not tossing out the L, if you wish. So what we need to do is our goal is to take that, well, see, have I written down the model yet? I haven't written down the model yet, have we? So this is just explain, this is, yeah.
So here have the definition.
Yeah.
That momentum accounts for curl of the magnetic, the angular momentum. Now we're comparing things that in principle, they have different scalings, because gradient of L, it should be 1 order lower than velocity.
Well, you'll see that it all works out.
The question is, do you retain higher order derivatives of
Okay.
L in the equation?
You can in principle, but those integrate to zeros. So if I go to the second order, then with all those gradients, it basically, it just doesn't contribute to the orders you want. Now you can ask, well, suppose I really am interested in that, then we can add higher order terms. In fact, we'll find this curl L misses one, and it's not so useful because we have a state that isn't actually ordering in the way it needs. So we'll see that in a minute here, how that goes. And yeah, so down here we have that the equation of motion for the total momentum does what you expect. It has a gradient of the current, which is the velocity times g itself, the total momentum density. Yeah. And over here, it's not equal to the same equation for the center of mass thing because we don't have the spinning term there. Okay, now, where am I? Okay, so what we need to do now is to develop a theory that really reflects that continuum theory I just showed you. How can we first develop a simple kinetic theory for the system, which is, what you would teach in your first year mechanics course, and then find a way of coarse graining that so we get the G plus a half curl L. So what you do there typically is that you're interested in fields that have some local variable that depends upon the particular particle alpha, and we convert it to a density by saying that, this function O of R has the value O alpha at the point R alpha. And then we want to coarse grain that basically by integrating over R prime of some averaging function W of R minus R prime times theta. Now, we can also write down a similar formula for the system that has O of R has A alpha, B alpha, both of them at the point R alpha. And we can show that what happens there is that you get O of R, that's the coarse grained thing, is AR, BR, N of R. And we find that there's virtually no combination of variables here that is ambiguous. You know that you will get this answer from the beginning. So the next step is to write down the atomic theory of what goes on. Okay, so here, yeah.
So coarse graining that you propose, there are various coarse graining procedures that you can perform. So what picks the right one?
Is it like?
Well, in our view, the right one is the one that correctly describes the long wavelength limit. But you may laugh at that, but here, this is let me discuss this slide because it sort of answers your question. The coarse-grained Hamiltonian for a system in which I decide that I really don't need to see the L itself, let's just put G squared over 2 rho. Now, that actually is quite an appealing choice because, you know, people who work in this in hydrodynamics of complex molecules actually say, well, the G itself has all of the degrees of freedom I'm interested in, and it ignores the fact that you have some constraints. So, you know, imagine that you have a collection of molecules that are a square, right? Then that thing actually has some motions that are cost you no energy if I have frictionless bounds there. But all of them have the rotational symmetry. So this guy really lacks what I need and gives the wrong answer. Now, I also was sucked into that, and there's a paper with Tomer and my name on it, which actually does it. And that pleases, I think, a lot of people, because if you have just this form and haven't broken it up, is you get the answer that you tend to get, say, in the superfluid systems, that the odd viscosity really is only that one component that we saw in the beginning. But that is, I mean, and you can see we've written it down here. What comes out of that analysis then is the total momentum has a stress tensor, which is all this in the square bracket. The eta E IJKL is from the external, well, it's the standard. I'm not sure why he used E there, frankly, but it's the standard dissipative viscosity. And then you have the eta naught, which has exactly this form right here, where you have the coupling between the compression variables and the shear variables. And but the difference is here now that, well, let me say this correctly. We also have the equation for L. Now there's one thing, oh shoot, I see Tomer forgot to put in an equation here. So you see this gamma omega I minus little omega I. The little omega I is the 1/2 curl V, and the omega itself is the rate of spinning of the molecule. And there should be another factor here of epsilon ijk gamma, the same gamma, so that if I solve for L, if I solve for gamma, then I get an equation that doesn't see the gamma, but sees the L. And that then gives you, when you go through the arithmetic, which is tedious, I mean, it's tedious arithmetic, but you do get exactly the predicted odd viscosity. Now,
These equations, the activity is only in tau I.
Tau is what's driving things, right? That's what's driving the spinning. And in fact, down here, we have a little note that when you solve for L from this equation to lowest order, it's the moment of inertia times tau divided by the gamma factor. And so this says that we have a lot of control over how fast we spin the things. And yeah, okay, so that should be clear enough.
So
Yeah.
here's my question. So this comes with this gamma, right?
Yes.
And I'm assuming that this rotation couples with the new velocity. The velocity that was done by shifting with respect to the curl of the angular momentum.
I think that's right, yeah.
But then, if that's the case, if I go back to the original one, this would have some Laplacian of my angular momentum.
So, no, the term we're talking about, let's see, where is it?
I think it's 11th slide.
11th slide, I'm sorry, way down here. Okay, so notice this equation appears in the equation for L dot, not for L. So I think that should take care of your question.
With omega there, it's already assuming that this modified velocity, it should be in drag with the rotation outside.
Well, as I say, I should be a term here that didn't get put in of a half epsilon ijk grad the gamma. And so that's where you see that effect in there. But it goes away when you convert it into being a function of L alone. Because it's mutual friction, which you don't see when you look at the total angular momentum. Okay. 11. 12. Oh, shoot. Now we're out of order. Let's see here. Oh, what has he done to me? I'm sorry. Okay, so what I should be seeing next. Yeah, so let's now ask what is the Hamiltonian for a actually I don't see where it is, so let me just write it down over here. I can use this here. So the Hamiltonian is now sum over the particles of P alpha squared over 2n plus L alpha I inverse L theta with the 1/2 here. And this is squared. And this is all you have. That's the model. Everything that you about the system is hidden in here. It's kind of nasty because you have 10 to the 23rd particles and all of that business, and you want to convert this into a coarse grain system. So we want this to go to an integral over R. And for simplicity, I'm just going to do 3 dimensions. I should go back and do 2 dimensions at some point. Okay, so following the rules we have there, this thing becomes 1/2 GC squared over M, and over 2M actually, but this should be a capital M. No, this will work all right. The mass is 2M, you have the 1/2, this is the GC squared, and then we have plus I L squared over 2. And this is a field now. Now, in the process of creating this, we actually then introduce some terms that have gradients in them. The surface things, and those are important in keeping things going. But maybe I can find in my other, excuse me here. I warned you're likely to have some of this stopping. Okay, so what's this guy? Wonder, can I close this thing now? It used to be I could close it, but they keep changing things. Okay, well, you can sort of see this. These are the terms we had before. This is the G spin, that's part, expressed in terms of the variable. So what we've done is to say that we can go back to the very beginning where we had where we defined the molecules to be. Can you see when it's over here? So what am I doing now? Yeah, so we set up our expression for G as the sum over particles alpha of P alpha 1 plus P alpha 2 and squared. So this is 1, this is 2, and there is a bar between them. And so the total energy really is the total energy of the system in the given particle. I'm sorry, this is, I erase this. I did this just a little too quickly. This is squared here and squared there. And then you set the P alpha mu, this should be. Well, that's what that 1 is. So we have P alpha is equal to P alpha 1 is equal to P alpha plus mu alpha A, mu alpha dot A with an M here. Well, let's write it a little more clearly. P alpha 1 is P alpha plus M A mu alpha dot and plus P alpha minus M A mu alpha dot. And that's what the total momentum is, and we wrote it out like that. And this leads to then for the Hamiltonian, P alpha 1 squared plus P alpha 2 squared divided by 1 over 2m is everything. But this guy is P alpha plus the mu alpha dot term squared plus P alpha minus the mu alpha dot squared. So you can see by choosing a good choice of variables, we have now, when we expand this out, there's a P alpha squared, there's a P alpha mu alpha dot, and there's the cross term P alpha mu alpha goes away, and you have a mu alpha dot mu alpha, which gives you the momentum. So I think I have that written down here. You can see it here. And once you've converted the mu alpha term put together, you have this double epsilon, odd factor that converts the nu alpha dot nu alpha into the angular momentum, I nu alpha cross nu alpha dot. And this Q alpha dot is basically the quote pneumatic order that would come in if you kept track of the nu, and I'm ignoring that for the moment. Okay, so let me just see now, where are we? How are we doing on time? 10 minutes, okay. Well, okay, so basically we've got all we need there. We can calculate the nu alpha. For the first theory, you get the actual odd viscosity expression. Now, when we go to the second theory, well, it's interesting to look at the mode structure of the one where we have just the G without the with nothing beyond the G, without the L term. So you get a 4x4 matrix like this. It has it has, gee, what am I doing here? So, that's an easy matrix to deal with. If you calculate out what the modes are with this one, it's precisely what you get when you have only the G present. Now, and so what the structure of that is there any way I can make this thing go away? Let's try this. There, that'll do. So there are 4 modes, and they all have some region where you have propagating modes all around, except for over here, these low frequency ones bend over, and you have a line where there is no frequency at all. The frequency is 0. Interestingly enough, this is almost identical to the modes of a columnar liquid crystal elastomer. Any of you know what that is? The liquid crystal elastomer. It's really an amazing subject. It's really an anisotropic solid where you have 0 modes in some directions and no 0 modes. This is the dispersion relation for that. So, I mean, this gives you what you expect. Now, of course, when you add the viscosity itself, the eta E, then you get damping, and it's a little more complicated. Right. Okay, so now if I go to the double coarse grained, this is what the free energy looks like, and you have this thing in blue, which is L cross nu, and that thing translates into a a term that's related to the L in this whole business. So the coarse grain version then can either be expressed in terms of the center of mass momentum plus the L, or you can express it in terms of the total momentum plus the L. And the difference between the two is that in this case, the L cross nu becomes a, where is it? It's an omega. Well, it's L cross nu there, right? But here we have, what happened to it now? Here we have a minus L dot omega term with the G total squared. And up here, it looks like we've left out, again, an equation which should have a plus L dot omega there. So, you know, it depends on whether it's GC or G. So now rather than getting the odd viscosity alone, we get the red thing here, which is the odd viscosity. And then we have this additional term, which is, what's the word I'm looking for now? That's right. That's what I'm looking for. Not reciprocal, right. So these non-red ones are non-reciprocal. And you can see it fairly clearly. So
it's non-reciprocal from the eigenvectors shown up in the eigenvectors of the
that's right. That you only see it in the eigenvectors, whereas for this case, well, okay, so for no epsilon E, you know, the real viscosity, it's obviously the case. You can see here that the only place that I see something that's different from the one with just the pure viscosity is this LR K perp term. K is a momentum and LR is the angular momentum number divided by 4 rho naught. And so that has what you want. When you add the extra components there, this is what you get for the just G term without the omega L terms. And now I want to go back to the other one because I didn't finish this one. So let me just see how we move along here. Well, so we should have concluded by now that the right one of these to choose was the one with the 2 modes in it, because let's leave that one for now. And here's what the mode of the full G squared plus the L squared term, and it has 4 modes. I think the note modes are becoming a little bit less interesting now, but basically you have things like this. L perp, L is the angular momentum density, eta perp is the viscosity, the actual dissipated viscosity. And so you have regions where the solutions are unstable, which means the modes involve exponential growth, along with, in the gray areas, we have stable things. So you can have, depending upon which axis you're choosing, you can have different forms, and you have these lines of where you go from having all of the modes on both sides of the line, but in the line itself, it's critical. So now I would like to take just the last 10 minutes here to talk about, let's see.
Oh, I'm sorry. I think you have 5 minutes. So
Okay, well, then I will zip through this quickly, I think. I hoped. Maybe not. Shoot, I really, no. I'm going to take, oh, I'm on Zoom? Why can't I?
you're trying to switch to the other presentation? There you go.
Yeah, now I've forgotten what I have here, the mode structure. So, no, okay. No, okay, I have to do something different here. Let me do this quickly. So there are two things you'd like to know about that we haven't covered here. And this is now in a PDF, which I couldn't copy. So just make sure I go through all of these right. Okay, one thing I'd like to ask, what happened to the other mode? You know, we said that we froze out a mode by having a rigid rod. And you would like to know what causes that. So you have this model of the mode that we're talking about. You have a spinning rod. Let's replace the rod by a spring. So I have here an energy which is the energy is R1 and R2 are the positions of the two balls at the end. So that expanding that out in powers of little r, where you have the separation of R1 minus R2 is A plus R. And I get an equation for the energy, which has the kinetic part, 1/2 mv squared, the kinetic part associated with the center of mass rotation of everything, the spinning part, which we've seen already. And now I have for the extra mode, a 1/2 m is the mass of the particle, r squared dot, or r dot squared, plus a 1/2 k squared. So we've converted this rigid rod into a spring that goes back and forth. So you want to choose out of this, as it spins, the r, there's a preferred direction which is larger than the original length of the rigid rod, because we've got centripetal forces that are separating the thing. So you find that the minimum energy occurs at RC is big omega squared over little omega squared over 1 plus little omega squared. And when all of that dust settles, you find that the effective Hamiltonian, where you've lost the mode where the thing was rotating rigidly, rather the compressional mode, where you now have the energy as a 1/2 the moment of inertia I squared times little omega squared over omega squared plus capital omega squared. So this provides not only a way of keeping the counting straight, but it shows that, in fact, you know, when you talk about the effective theory of a system like this, where I only have the g squared parts and the p squared parts, right? This actually renormalizes the effective constant of the compression there, which I think that's kind of neat. It shows that you could imagine now creating, this creates for you a theory where you've integrated out the variables that are fast. They do not come down to zero energy when the wave number goes to zero. And well, you expect that to happen. So you could even imagine fixing up things here so that you've got an LL interaction in the system, or an L to the 4th energy in the system, which would give you a phase transition maybe. So I think since I only had a minute left a little while ago, I now have none left, and I will close. Thank you for listening.
You need quick burning question? Nothing burning.
Okay.
Thanks. Okay, I think Alan is next. But there's a trick to make fast PowerPoint slide by cutting out from figures that I'll show. There's a 3-button combination that takes snapshots.
Oh, really? Well, I mean, that's what I was doing.
No, but you were trying to copy text. You don't, I'll show it to you. No, don't copy equations, copy pictures of equations. Yeah, I'll show you.
That's what I was doing.
No, but based on what you showed, it seemed like you were subjecting yourself to the whims of Windows fonts. My hack is, yeah, just it's a simple. I discovered it during the pandemic because I had to make my lecture slides very quickly. So I think the snapshot sort of feature.
Where I don't see it anywhere.
It's Windows Shift S.
Windows should.
And then what you see is that your screen then changes thing and you can just drag out a portion of the, whatever you want.
You have your PDF on.
Yeah, well,
Acrobat
it's easier to
Reader,
show.
You can do it under.
All right. So I have
Are you on
Zoom. I'm on Zoom.
Use,
Let me get my, let me get my,
disengage your audio, so there's no echo.
disengage. My audio is off.
Well, I think, yeah. This is, because the micro, you don't, this is how you make sure the microphone is off.
Okay.
Now you share,
Okay.
where's your?
Let me find my talk.
Oh.
Certainly.
Panel, is it?
But I mean, if you're on Acrobat Reader, there's like a little.
Let's go back to Zoom, sorry, just make sure that it's shared properly.
Sure that that's.
Nope, I didn't see.
Should work, and then, I mean.
Hang on.
it's not highlighting-
Hit share again.
highlighting the proper. You need to like, I put a box around it.
This one?
Yes.
Okay. I think we're good.
And it looked like I.
Are you
Yeah.
happy with this? Or do I need to do anything to the?
Looks good. Is this,
All right.
so Vadim, the slide advancer?
You might have to stick that in somewhere. It worked for others. I'm actually shocked that it's working, because it's not mine. I don't mean to. It happens to sometimes.
Does this
things
have a
work.
pointer as well?
It had a pointer. Yeah. Oh, maybe it doesn't anymore. Well, just a second. Maybe batteries here. Okay. See if I can push my lock. These, yeah. But let's see, since people use this already, let's see if the universe keeps cooperating. Oh. Is there on off switch? Maybe somebody tried. People used it. No, I don't know, but does it even update?
I'll make it
Okay.
work.
Sorry,
It's okay.
it worked for others. I have no idea. Okay. Sorry. There is a stick.
Yeah.
All right, shall I go?
Okay, can we,
Okay, well, good afternoon, everyone. And I'm going to join the chorus of thank yous to our organizing team who seem to be doing everything here. I'm really impressed by their energy. So thanks so much for putting this meeting together. It's interesting. I'm going to talk a bit about super solids today. This is some old work that I did over 12 years ago. So I was last here at the CUNY Graduate Center for a conference on supersolids in 2011. And I think we may have been in this room. It seems very familiar. And amusing anecdote, as part of the conference, for the conference banquet, the organizers had organized for the group that we go on a dinner cruise down the Hudson River. They would take us down to the Statue of Liberty and around the southern tip of Manhattan. So we went down to Chelsea Pier. We all got on this boat at 6 o'clock, and there was dinner and dancing. There's several groups on the boat. So we got on the boat. All the physicist nerds got onto the boat, and our hosts on the boat, the captain was going around and welcoming all the different groups on the boat. And so finally they got around to the super solids group. And he said, well, we especially want to welcome the super solidarity group. So they somehow thought we were like a labor activism group there. And there was sort of power to the unions. And so that was just amusing. So super solidarity. So this is work I've done over the years with
John Toner, Paul Goldbart, some of my graduate students who've now moved on to other things, Chi-Gyuk Yu, Kinjal Das Biswas, Debaja Goswami, and also some current work I'm starting to do with Leo Ratzhofsky as well. Now, let's see. I'm having trouble advancing my slides here. Let me take this out.
Yeah, maybe that's interfering.
Well, that's weird.
It's like, is your whole computer frozen or just this part?
Let me escape.
Okay, that's good.
And now try again. So I'm not sharing anymore.
I just said, first name. I don't know what the problem is. Stop video to make it easier. We don't need that. Oh, you closed the whole thing. Okay.
Yeah, so let's open on that one.
Oh, it's still, okay, all right.
And now,
You can share that. Oops,
and now we,
that's a PDF. If it's PowerPoint, then that should share it. No? I'll let you do it. We don't need that. You will probably want to go full screen.
okay,
Okay.
back, let me see. There we go. Okay, so often when I travel, people ask me where I'm from. I tell them I'm from Athens, Georgia, and they have no idea where that is. So I often prepare a very short geography lesson for audience members. So I'm at the University of Georgia, which is in Athens, Georgia. So for those of you who've not had the courage to venture south with the Mason-Dixon line, there's the state of Georgia in red. But let me blow that up a bit. Here's Georgia. And as a map, I've taken the 2020 presidential electoral map to sort of illustrate where the population centers are in the state of Georgia. So, so the big blue dot right here is, of course, Metro Atlanta, about 5 million people. This little smaller blue dot out here to the east is Athens, Georgia. Okay, so the university towns can be clearly seen on the electoral map. I just thought that was interesting. Athens is well known for many things in addition to the University of Georgia, and I think if you know anything about Athens, it would be because of our music scene. So we were where the B-52s got started back in the 1980s, and as well, our Fab Four from Athens, REM. So, and REM ties into the talk we had about vision earlier in the day. So there are some connections. Okay, so my outline is, I want to talk about supersolidity, not super solidarity. Supersolidity, so can Bose-Einstein condensation occur in a solid? I mean, that's really the question. And I'll give you a brief history of both superfluids and supersolids as well. How would we know if we saw a supersolid? I mean, what are the signatures of supersolidity? And I'll also talk about some very beautiful work that's occurred over the last 5 years in which there are observations of supersolidity in dipolar Bose condensates. And I'll talk about hydrodynamics because this is a meeting on hydrodynamics, and so I'll have to get that in. So I'll talk about what I guess we would call now an effective field theory that gives us the hydrodynamic equations of motion for a supersolid. And I'll build up to that by going through a mode counting exercise, which will be very familiar to some of you, but I'm suspecting not so familiar to others. And everything I know about mode counting, I would owe to Tom Lubensky, having read his book very carefully years ago.
How many times?
Many times, many times. So I'll go through mode counting, and then I'll talk about our variational approach to supersolid hydrodynamics, how to derive a Lagrangian description for a supersolid, using a construction to build in the various symmetries, which is known as Clebsch variables or Clebsch functions. Okay, so the question is, can Bose-Einstein condensation occur in a solid? Well, it occurs in gas and liquid phases and dilute atomic gases, and it occurs in superfluid helium-4. So can it also occur in a solid? And so, perhaps stated differently, can off-diagonal long-range order, we just call that Bose condensation for short, coexist simultaneously with shear rigidity in a solid? And actually, more specifically, I want to just focus on crystalline solids. So I won't talk about glasses, but maybe that's a separate issue. One could talk about super glasses. I don't have anything to say about that. So the naive or the quick answer to the question, can Bose-Einstein condensation occur in a solid, would be no, because one imagines that for a Bose condensate, one has very sort of delocalized wave functions, lots of overlap between particles, and that gives rise to the condensation. And in a solid, we imagine the sort of a Wannier description of very localized wave functions, very little overlap. So it would seem unusual that we would get a Bose condensate out of such a system. So, but okay, that's the quick answer. Is there a longer answer? So it could be yes, there could be a Bose-Einstein condensate in solid. So let's turn to the theorists and see what they have to say.
So this is different from vortex crystals.
Different than vortex crystals in Bose-Einstein condensates.
You have a rotating DC, you can create
Is that would I consider that to be a super solid? I'm not sure I would. So, I mean, one thing I should have said is that when I talk about a super solid, I'm with the crystalline order, we have translational invariance, which is spontaneously broken. So I'm not talking about a supersolid that might exist in, say, an optical trap where we have some periodicity that's been imposed by the lasers we set up and so on. So it would be a situation where the particles that crystallize are the same ones that are participating in the Bose-Einstein condensation. Would that be the case for a vortex lattice? I don't know the answer to that offhand. Yes, Vadim does.
No. Well, I mean, I don't care. No, but just, I want to just clarify something, because I recall from when, you know, from a while back when this was, once again, contentious, being really confused about the rules about asking questions and answering them, because I feel that certainly in the domain where you have lots of degrees of freedom. For example, if I take, to be very specific, niobium diselenide, which is some kind of a metal, which occurs as you lower the temperature.
CW.
It develops a charge density wave without gapping out the entire Fermi surface. And as you keep lowering the temperature, because you have metallic degrees of freedom, the charge density wave is just whatever, it's there, it's the background, and then the remaining conducting degrees of freedom, they go superconducting. So you have a coexistence. So the coexistence of the Fermion answer to this thing is that yes, and yes, these things always exist, and so what's the big deal? So I feel like in the helium kind of domain, it's more mysterious, because you have to make these conducting degrees of freedom as vacancies interstitial, so it's a little bit more mysterious because of historical, you know,
Sure. Okay.
factors and not physics.
Okay.
In some sense.
Yeah, I'm not sure I'm going to make it any less mysterious
Yeah,
today.
but can you clarify? Because I feel like depending on where you come from, this question is utterly.
Either trivial or really subtle.
Yeah, yeah. Well, what's the issue?
I think it's actually very subtle.
Well, immature sort of a perception.
Yeah, so would the coexistence of superconductivity and a charge density wave in niobium diselenide constitute a supersolid? And I think the answer is, I would say no. I mean, the electrons that are participating in the charge density wave, or I mean, are they also superconducting? I've not thought about this particular question. So let me, okay, we'll come back to that. All right. So the history of this particular problem is a long one. It goes back almost 70 years to a very beautiful paper by Penrose and Onsager. So Oliver Penrose is Roger Penrose's older brother. And they show many things in this paper, but one of the sentences that would catch your attention if you're interested in supersolids is they say very clearly is conversely, it is shown why one would not expect Bose-Einstein condensation in a solid. Flat out, it doesn't exist in a solid. So that's the work of Penrose and Onsager, 1956. Okay, let's fast forward to 1970. So Jeffrey Chester is at Cornell University, said, well, it's not so simple. And it's not so simple because the work of Penrose and Onsager was really focused on a commensurate crystal. And if you allow for the possibility of vacancies in your crystal, then Chester's work basically says, well, the proofs that are embedded in the work by Penrose and Onsager are all off. And in fact, Chester suggested that it should be possible to have a coexistence of Bose-Einstein condensation and solidity in a crystal which had some vacancies in it. And so I've underlined that a quantum crystal can only have a Bose-Einstein condensate if it has a finite fraction of vacancies. So that's interesting.
So are there any calculations done?
Yes. Yeah. So, I mean, I would say proofs of principle, which I can come back to. I mean, there's a suggestion that, so with any collection of bosons, the ground state wave function is known to be nodeless and also can be made to be real. That, I mean, that's, I think Feynman probably proved that. What Chester showed that if for instance, you approximated your ground state Bose wave function by a Jastrow wave function, so two-body correlations only, that can be mapped into an equivalent thermal system of a set of particles interacting. And his argument was, well, if you lower the temperature enough, we know that those particles will eventually crystallize. So, and if the equivalent classical system is at some finite temperature, there's always a possibility of there being vacancies there once the temperature is greater than the vacancy condensation energy. So it was kind of a proof of principle that, you know, not that a Jastrow wave function is a good description of liquid or solid helium, but there was a possibility. So kind of a brief detour to talk about vacancies and interstitials. So you can have local density changes in a solid, which can be due either to local compressions or dilations of the lattice. Okay, so we have a displacement field U, and the divergence of U tells us about the local volume change in the vicinity of some point. So right here, I've tried to illustrate that with this hexagonal lattice. So there's a change in density, which is proportional to the divergence of U. Or we could fix the displacements and just pluck particles out or put particles in. So we could create vacancies or we can make interstitials. And in general, density changes will involve both the existence of vacancies and interstitials and lattice displacements as well. And that's an important point because density fluctuations in general in a crystal are not slaved to the displacement fields. It's a separate degree of freedom. Now, at about the same time, so the Chester paper was published in 1970. There's another very beautiful paper published by Andreev and Lifshitz in 1969. And I had somebody ask me the question that, did Chester know about Andreev and Lifshitz? I think the answer is no. I think that was at a time when it took a while for the Soviet literature to make its way to the West. And so my guess is that there was no communication about this. But at about the same time, a beautiful paper by Andreev and Lifshitz that basically suggested that at sufficiently low temperatures, localized defects or impurities change into excitations that move practically freely through a crystal. So that there should be a kind of superfluid that moves through a crystal, a quantum crystal. Well, how would you see this? So there was another very interesting proposal in 1970 by Tony Leggett. And Tony suggested that one should look for signatures of what's now known as non-classical rotational inertia. And this is the same thing that one uses to look for superfluidity. And the idea is that you take your quantum crystal and you rotate it. It has a moment of inertia. And then you change some parameter that you think will induce it to become a supersolid. And the most likely parameter to change would be temperature. So let's say you lower the temperature and you believe that you move from a normal solid phase of the solid helium into its supersolid phase. In the supersolid phase, we suddenly have a superfluid of these vacancies, which don't participate in the rotation of the solid. So there's a sudden change in the rotational inertia. So he referred to this as non-classical rotational inertia.
Is it like Andronikoshvili effect in the helium?
It is, correct. That's right. But, I think this is important with thing I'll get to in a bit. I think the response of a liquid and a solid are quite different. And I think this confused many of the experimentalists, confused many physicists. I add myself to the group. I won't separate out the experimentalists. But I think it's actually more subtle in a solid because of the sheer response of the solid. So that was the way to look for it. So there were, before I go on, I wanted to talk a bit about helium. So helium is soft matter. For those of you who've worked on helium and you want to call yourself soft matter physicists, I think you're entitled to do so. I consulted with some of my experimentalist friends about some of the properties of helium-4. So it's very soft. So it has a shear modulus of about 20 megapascals. And I asked my friend, well, what does that compare to? And he goes, well, it's like butter. He says, so helium's like butter. It's like cutting butter. So well, that's interesting. It's also it has very low density. So 0.2 of a gram per cubic centimeter. So it's a bit like cork. So it's very light. It's very soft. This is the phase diagram for helium-4. So this is the normal liquid phase. The liquid gas critical point. There's the lambda transition, second order transition, separating the normal fluid from the superfluid. And then if you pressurize helium to a pressure of about 25 atmospheres, you can coax it to become a solid. So there's a solid phase up here. It's a hexagonal close pack. There's a little sliver of BCC there as well. So it's also a material that has a very large de Boer parameter, which is something that suggests that quantum effects are going to be very important in helium and much less so than, let's say, solid argon. So quick question.
For those of us who don't think about this, what are the and sigma? What is the work parameter?
Oh, this Dvory wavelength, and sigma is the hardcore radius. So if there's an effective hardcore radius for the helium atom.
Gotcha.
Sorry. Okay, so there were searches for supersolids that went on from the 1970s through the 1990s. And a colleague of mine, Mark Meisel, wrote a nice review article about all those experiments. And I can send you the reference if you're interested, but they were basically all null results. Until 2004, when a group from Penn State led by Moses Chan announced that they had observed non-classical rotational inertia. This is the characteristic that Tony Leggett had pointed out to look for in samples of helium-4. And this hit the headlines. So I've extracted a graphic that was in the New York Times. I think it's the best graphic I've seen yet of kind of demonstrating what NCRI is. They have all the New York Times money to put behind getting the graphic together, but just illustrates the experiment. This is the torsion cell. In this case, what Moses is doing is oscillating the cell back and forth and looking at the response and doing that as a function of temperature and seeing if at some point there's some anomaly in the moment of inertia, some change in the moment of inertia. So they did that both for helium-4 and Vicor glass, also bulk helium-4, so one article in Nature, one Science, published in the same year. And subsequent to that work, there was lots of activity, experimental activity by groups, not only at Penn State, but at Cornell. John Reppy at Cornell was doing this work at Rutgers and in Japan and Korea as well. All these groups saw an effect. It's a very small effect, however. So lots of excitement in the community. And so here's some data, and I'm going to have to accelerate. This is data from one of the Penn State papers in which you see shifts in the period of the oscillator, which is related to changes in the moment of inertia, since the period of the oscillator is proportional to the square root of the moment of inertia. And so you can see you lower the temperature. This is as a function of temperature. You lower the temperature, and at some point there's a fairly, I wouldn't call it abrupt, but there's a drop in the period, which is attributed to a change in the moment of inertia, and therefore for some decoupling of a portion of the mass in the oscillator from that was being oscillated. Lots of details here that I don't really have time to go through. There is a critical velocity. So as they increase the frequency to higher and higher frequencies, you can see that eventually the effect goes away. So it appears that there's a critical velocity as well, just as there is for superfluid helium. Now, to put in a shameless plug for some work that I did years ago, one of the things I wanted to do is see if there was a simple Landau theory for a supersolid. And how do you do that? Well, you have to think about all the symmetries of the problem and how they are broken in all the Goldstone modes. For just good old-fashioned superfluid helium-4, this is our U1 gauge symmetry that would describe the transition from, this is in 3 dimensions, the transition from the normal phase into the superfluid phase with all that, with the lambda anomaly and the specific heat, all those good things. In a supersolid, we also have to take account of the elastic degrees of freedom in the solid and think about how they couple to the order parameter. And so the simplest coupling is just this coupling I've written down here, which is coupling the strain tensor to psi squared. That's the lowest order coupling that's allowed by all the symmetries in the problem. What this becomes effectively, it's a compressible O2 model, if that makes any sense to you. So it's like a spin model on a lattice with O2 spins, but where the lattice is compressible. The lattice, the couplings between adjacent spins can fluctuate. So what we did is we looked at, we wanted to ask the question, okay, let's do some phenomenology. If there's truly a supersolid transition, shouldn't there be signatures of that in various properties like specific heat? But also, since this involves a lattice and we're compressing it or we're expanding it, maybe there are also anomalies that crop up in the elastic constants as well. And so we worked all that out. Never saw any of it in any experiment, but it was still a fun thing to do. And that was work, in case I didn't mention it, it was a flock of us since John Toner was involved. It was work I did with John Toner and Paul Goldbart. Paul was here yesterday, but I think we'll be here again tomorrow.
But I would think that these singularities are required to be there. So the reason experiments didn't see them presumably because they're discrete.
Well, that was the explanation oftentimes, yes. Or they were smeared out by various defects that include things like dislocations. So we didn't see, there wasn't much signal in the bulk helium. We thought, well, maybe dislocations in the solid play a role. So then we spent some time trying to figure out what a Landau theory for a supersolid looks like if we put dislocations into the solid. And so those dislocations in effect become like tubes for a Bose condensate. So and there's a way then, there's actually something called the Shevchenko state that was proposed back in the 1980s for superconductors, where you have a network of these dislocations, they overlap, and it becomes, again, a bit like an XY model. And this sort of percolates through and you get a transition through that random network.
This is Kalman disorder.
It would be,
Kalman TC
it would, well, you could have both edge dislocations, which is what we focused on. You could have screw dislocations. In these particular solids, HCP solids, they get mixed as well. So
yeah, I guess I'm just, I don't remember, is this sort of supposed, yeah, is this system Harris stable against this kind of Kalman disorder?
I think the answer is yes. Okay, so we didn't see anything there. I should say over the intervening years, there were more experiments done. And one of the things that came out is that if you took the helium out of the torsional oscillator and just tried to measure its elastic moduli, it was discovered there was a significant temperature dependence to the elastic moduli as well, which was a little unexpected. This is not an experiment that would have been done, but there was significant temperature dependence, in part having to do with complicated dynamics of dislocations in this quantum crystal. In the end, it was eventually concluded that the original signals that were attributed to mass decoupling were probably better described in terms of some changes in the shear modulus of the solid helium. So the way I used to talk about this is we didn't learn much about supersolid helium. We learned a lot about what I called quantum metallurgy. So metallurgical properties of solids at very low temperatures where maybe quantum effects are kind of important, but I don't think we learned a lot about supersolids. And so this is the original paper by Kim and Chan in 2004. And then in 2012, a second paper by Kim and Chan, same Chan, different Kim. But you can see the second paper entitled Absence of Supersolidity in Solid Helium in Porous Bicore Glass. So basically at that point, Moses is saying it looks like everything was due to the elastic properties of the solid helium, and we can no longer sort of attribute these changes in the moment of inertia to a possible supersolid phase. So 8 years of work, and this is the outcome. I'll also say in 2012, I became Dean of Arts and Sciences at the University of Georgia. So I decoupled from this work as well. And I stepped down as Dean last year and tried to re-engage with my research. And so one of the first things I did last summer is I thought, well, I wonder what's going on in supersolidity. So like Rip Van Winkle, I woke up from my long administrative slumber and came back and found a lot of exciting work in supersolidity. So I should have written Long Live Supersolidarity, but there's a really exciting work that's happened over the last 5 years, and I won't have much time to get into any of the details, on dipolar Bose condensates. And these are, I refer to them as quantum ferrofluids. So there's dipolar condensates where the dipole-dipole interaction, at least if you do it for planar traps, leads to modulated phases, not unlike what happens in ferrofluids. For those of you that have played around with ferrofluids or in thin magnetic films, you can get various kinds of phases, including stripe phases. You can get meandering domain walls in a thin magnetic film or a ferrofluid, or you can get bubble phases where a ferrofluid, and for those of you who don't know what a ferrofluid is, it's It's a colloid of manganite particles. They don't agglomerate, and they can align, and they're really fun to play with. And so if you ever have a chance to play around with ferrofluids, I advise that you do.
It's in free space, no lattice.
And these results are in free space, no lattice. Yeah.
So the periodicity is macroscopic. This is not like, periodicity is basically the aspect ratio business of that whole structure.
Well, it's set by the dipole-dipole interaction, competing with short-range repulsive interactions. There's so-called LHY interactions, which are kind of beyond fluctuation contributions. And this is what's observed. Really excited. I'm going to highlight a paper here by Johannes on superfluid smectics that came out a couple of years ago, but I think there's a whole new range of exciting problems that one can work on as a consequence of these recent experiments in dipolar atomic condensates. So I have -2 minutes, it looks like. Is that right?
But it's coffee time.
But it's coffee time. So, okay, thank you. So just a few comments. So I already said some of this. So the dipolar interactions lead to these modulated phases. And these occur in lots of different systems as well. So, you know, not just ferrofluids, but Tom, help me out. What are some other good examples of dipolar interactions? I think phospholipid bilayers is another example. There are a whole bunch of these that are exciting. There's a nice overview of this work, the experiments, actually a Physics Today article published in March of 2022, if you want to figure it out. So let me quickly go through hydrodynamics, and I'm going to zoom through this. I'm going to do mode counting. So I want to construct a hydrodynamic theory, or I guess we would call it now an effective field theory for a supersolid. How do I do that? Well, let's start by thinking about what the necessary ingredients are. With a simple fluid, I want to construct a hydrodynamic model. I need to account for the conserved densities. And so for a simple fluid, those would be the energy density, the mass density, and 3 components of momentum density. So I'd have 5 variables. I write down equations of motion. Those give me various modes. And what are the modes? So I have 5 hydrodynamic modes. I get 2 diffuse transverse momentum modes. This is a liquid, so there's no shear modulus. I get 1 longitudinal thermal transverse mode, and I get 2 longitudinal sound modes. Omega goes as plus or minus CQ. So one in one direction, one in the opposite direction. Each of those is counted separately when you do mode counting. So those are the 5 modes accounting for the degrees of freedom. And you see these in light scattering. If you do a light scattering experiment where you couple to density fluctuations, you see the central Rayleigh mode and the 2 side Brillouin peaks as well. Okay, what about a superfluid? Well, now we have an additional broken symmetry, which is the U1 gauge symmetry. We have to put that in as well. So now we have 6 quantities we have to account for, and we expect 6 hydrodynamic modes. What are they? Well, we still get the 2 transverse momentum diffusion modes. We get 2 longitudinal first sound modes, but now we have 2 longitudinal, what we'll call second sound modes, which is this thermal diffusion mode basically hybridizes with the Goldstone mode to lead us to these 2 second sound modes, which are propagating modes.
It looks like more like a 2-fluid model.
That'd be like a 2-fluid model, correct. And same thing here. So this is a light scattering from a superfluid. You can see the central Rayleigh peak. They plotted this in the wrong way, in my view. So this is high temperature reducing to low temperature, but you can see the central Rayleigh peak. As you lower the temperature below, T lambda splits into the 2 second sound peaks. So you see this directly in light scattering. All right, what about a solid? If we do hydrodynamics for a solid, what do we get? Well, okay, not for a supersolid yet. For a solid, we have density, 3 components of the momentum, energy, and then we have broken translational symmetry. So we have the displacement fields in 3 different directions, in 3 dimensions. So we have 8, we have 8 either broken symmetry variables or conserved quantities. We expect 8 modes. What are the 8 hydrodynamic modes? Well, 2 pairs of transverse sound modes. Now we have a non-zero shear modulus, so we can get transverse modes. That's 4. A pair of longitudinal sound modes, just like we had in liquid. That's another 2. And a thermal diffusion mode. Well, that's another 1. So that's 7. So we're missing a mode. And what is the missing mode? Well, the missing mode, this was really another brilliant piece of work by Martin, Parati, and Pershan, which pointed out that to really have a complete description, hydrodynamic description of a solid, one has to account for the presence of vacancies. And so you put that back in, and then you get all the modes you need. You get oops, that's super solid. In addition, you get a vacancy diffusion mode for a normal solid. But now for a super solid, finally, I have to add on top of those 8 modes an additional broken symmetry mode. And so I'll have 9 modes. The mode counting will be, well, 2 pairs of transverse sound modes, a pair of longitudinal sound modes, a pair of longitudinal, what we would call 4th sound modes, and a longitudinal thermal diffusion mode. The 4th sound mode is, again, a hybridization of what was diffusion of vacancies with the superfluidity. So that's the 4th sound mode. And yeah, so that's the mode counting. So how do we construct? I'm going to wrap this up in just a minute. So what we wanted to do is construct a Lagrangian description for a supersolid, kind of being inspired by mode counting. We did this using a technique that's often referred to as using Clebsch variables or Clebsch functions to implement various conservation laws or broken symmetries in the problem. And the upshot of that, we have a Lagrangian, so I guess we would call it our effective field theory, which describes both the superfluid degrees of freedom, described by this phase phi, the normal fluid degrees of freedom due to the lattice, and then their interaction. And the interaction is effectively a current-current interaction. So then there's the normal current and the supercurrent. And that's how the superfluid, what's that? The lattice is buried here and in here in this displacement tensor, and as well, Vn is basically R sub I dot. So it's just a
Negativations are in it.
yes, they are. Yeah, correct. That's right. So we would have to specify a constitutive relation that is embedded in F that we then expand to second order in displacement fields, and depending on the crystal structure and so on to get the full structure. That's the form, is basically Bose-Einstein condensation, normal fluid, and then coupling, which is a current-current coupling. How can I understand it? Oh gosh. I mean, it came out of I don't have a brilliant, it's an allowed coupling. I mean, one way to think about it, Vn, so in terms of displacement fields, that's just U dot, displacement field of the lattice. So it's U dot grad phi. You can integrate that by parts if you prefer. It could be gradient of U times phi dot. It's the lowest order allowed coupling, but it also comes out of this analysis using Clebsch variables that I mentioned before as well. One of the symmetries we impose with Galilean invariance, and that pins down the fact that this coefficient here of the Vn dot Bs coupling is rho n. I don't know. Good. So this is our work. I'm going to fast forward. We calculate the density incident response function. It's messy because now we have lots of degrees of freedom. I'm not going to dwell on that. One advantage of this variational approach that I like is it's a good starting point for thinking about defects in the supersolid. Because we want to look, one question is, what does a vortex look like in a supersolid? We know what a vortex looks like in the superfluid. In the supersolid, vortex generates transverse currents. But there's a coupling then to lattice degrees of freedom as well. How does that work? Does the lattice mediate interactions between vortices in the supersolid? So we're actually able to at least write down an effective action when we include vortices in our supersolid, and even if you want to get really messy, edge dislocations as well, and the coupling between vortices and edge dislocations. It's kind of a big mess, but there you have it. Ongoing work, I would say. So I'm just going to summarize. Supersolids are interesting. So I think there was the earlier question about why should I be interested? And well, I find this interesting, fascinating, but I mean, perhaps not everybody does. So I think this competition between off-diagonal long-range order and crystalline order offers lots of opportunity for thinking about new phases of matter, how those phases interact, what the dynamical signatures are, what are various topological defects, vortices, dislocations, what do those look like? And I think in dipolar atomic condensates, that may turn out to be a really interesting playground for thinking about lots of these problems. Thank you.
We take a coffee break now, so in the interest of time, I'm the only one asking. So I have one question. So
Sure.
typically, there is this Ramakrishnan's theory of freezing
Yes.
transition, right? So, but then you had a phase diagram where you can go from superfluid to supersolid.
Yes.
Is there a superfluid? Can one think of a superfluid version of that freezing transition? And think about
This
that?
is like a Verlet-Hansen theory as well. Is that? I'm going to ask our theoretical chemist here. Is
I
that?
mean, it's,
is it-
you just construct
Yeah.
free energy functional with respect to density, so you would have to do a quantum version of
Yeah.
it somehow. And remove the viscosity you need.
Yeah, I've never seen that done. I mean, I will say one thing with the dipolar atomic gases is if you do the usual recoupling Bogoliubov approximation, find the spectrum for the excitations, it's at least in weak coupling, it's very featureless. If you put in the dipolar coupling and you put in the Fourier transform, the dipole-dipole interaction, what you discover is you get a Roton dip. And as you crank up the size of the dipole-dipole interaction, that Roton dip can eventually hit zero, which suggests a soft mode and maybe a hint of kind of crystallization that occurs. There was some notion that this might happen, but a nice paper by Nozier about 20 years ago on connection between the Roton dip and solidification and healing.
Okay, let's thank Alan again, and coffee break, and we'll convene at 4. Christopher.
Sure.
I mean,
Like thermal diffusion.
Yes.
When you counted modes.
Yes.
In the classical case, there's also a regime of forming hydrodynamics. Right? If you
Yes.
have one cloud, and so you
I ignored that.
Regime, so
Yes.
you assume that there is enough unclog to kind of.
Yes, I think that's right. Yeah, I think that's right. Yes. Right. There's second sound in the phonon gas as well. That's which I always found puzzling. I never really understood it completely. I mean, it always seemed to me like there's some equilibration issues with that, but that's not completely clear.
Newton's power law, right?
Yes.
As opposed to exponential.
Right. Yeah.
Okay.
Yeah.
And for the same reason, when you counted modes.
Yes.
in the super solid, you still got thermal diffusion as opposed to this.
Yes,
So it's a mass transport to superfluid, but entropy transport, you assume that this.
that's right. So, I mean, if you take the linearized hydrodynamic equations for the supersolid, and I mean, you can see the hybridization between the density fluctuation and the lattice degrees of freedom, and the density fluctuation has embedded in it the vacancies. So, yeah.
And
So-
another very
Sure.
vague question. You counted two pairs of transverse modes,
Yeah, the two different directions.
but why pairs? Well, why just not consider each polarization as one mode?
Because they're propagating as well. So the way this is confusing. So with the longitudinal modes, you get two modes. You get omega is plus or minus CQ,
Ah, that's fun.
and you
In the crystal, it would be plus even less. In 1D,
yeah, I'm in a continuum
Ah.
limit. So I think it's like just for the simple fluid, you get omega is plus or minus CK, and the omega is CK counts twice because you have modes in opposite two different directions. If you had a chiral system and you only had a mode propagating in one direction, you just would count it once, but you have them in both directions. And with the transverse modes, same thing, because you get a transverse shear wave in two different directions, but they can go in two orthogonal directions to the direction of propagation. But that direction of propagation can be plus and then minus as well.
But if you just kind of go continuously, it's not a different branch. It's all about down. So I'm not
Yeah,
wrong about
yeah.
kind of thinking about.
No,
Q plus minus.
Yeah,
whatever,
yeah,
That's.
Okay, so maybe what I should do.
Yeah. Hi.
I think I just calculation of
Huh?
the basically different modes. Is it done in Doppler gas for Doppler gas specifically, or?
That's it was sort of a general result for any system that you're trying to describe with a hydrodynamic model.
But it would work also for.
Sure.
Uh-huh.
Now there could be things like anisotropies and
Right,
so on that come in.
So because of these dipoles, but they're probably not polarized.
Yeah, well,
Are they?
I think that's probably a knob you can tune with an external field. I mean, usually when people do the calculations, I assume they're all aligned.
Uh-huh.
They can't.
Right.
And if they can't, you'll get some anisotropy as well.
There's also degree of freedom, which is the like oscillation of the dipole.
Right now,
I think you can get it
Right.
yeah, so I don't know. I haven't thought about that. It's a good question. So,
Yeah, I was wondering, so in this cold gases, they can also do Josephson effect. And I
Yes.
was wondering for supersolids. Has it been?
that's a good question. I don't think it's been done.
Mhm.
But I think there are good reasons to try to do it. And in fact, for the superfluid helium, before people gave up on superfluid helium, there was a very ambitious proposal. It wasn't for the Josephson effect, but it was to make a big annulus of helium and just spin it.
Right.
So make a gyroscope and to see what happens. And that they never did that. But I don't think there was anything equivalent to that I'm aware of to a weak link for us for the solid case.
Right, but superfluids they do things like they can be like interference with DECs.
That's right, yeah. That's right.
But for supersolids, it's interesting because I don't know if dislocations in tunnel, for example, it's like
Right.
something.
Yeah, all new excitations, that is, I think, fun to think about. Yeah, sure.
Yeah, so that's what the name matters.
Wow.
Yeah. All right. Now, I figured PowerPoints will look very professional.
That's where I gave up.
I do that when I'm sick and tired of writing out the equation after. I just do that. Yeah.
He discovered that.
You can do, well, you can do LaTeX on.
Right, but maybe you're right. So I discovered some research. Simple math, which,
Yeah.
it's basically AI system. You can hit the handwritten notes, equations, and you can scan it in math. And it converts it.
I didn't know that. And then you can just paste it.
Yeah, yeah, and it,
But if you put
it's
it-
really, it works really well.
I'm already have like the equation.
Yeah. But I have all these holes here in those here. I mean, I like to type those up. I don't know what's going on. And there's some errors in there,
Right.
but it's like a 90% correct level. It's pretty impressive. So even though it's correctly interpreting mathematical symbols, so it's beyond, you know, what it is. Well, yeah, there's.
I have to remember, I have a quick question about your platform. I remember all of this, you know, there was, or, you know. What is that? They always. Yeah. Royer, maybe they thought that there was something living along the.
That's right. They found that it's
But then there was some people saying, no, that's wrong. Not more recently, but
yeah, that, I'm not sure. I mean, you were working with the edge system. They seem to be super friendly. They work with Swedish stations.
Which, yeah, okay. I mean, it's like, it's hard to do that because you have to do a finite temperature of PIMC. And that's hard. Diffusion microcontroller is much more easy, but then you're strictly at 0 temperature. And maybe it's not accurate, it's not controllable.
One of the things that got out of that is they were actually able to calculate the vacancy creation. Much larger and suggests that probably weren't.
I mean, I always thought this is, you know, you can ask the same question, why is our hydrogen not super fluid? On it, you know, at the pressure, and it's just the air interaction is too strong. So helium is just weaker by like. Maybe it's just all comes down to that space. Yeah, exactly. Chemistry. Anyway, I like it. Thanks.
Oh, there was that.
But again, it's not like key to like the quantum part.
Well, yeah, well, it's a good point, which is more about service. But I've always asked to say.
Yeah, so, so you're getting to give. So after each one, as far as the last one is sure. It's basically.
Okay, I couldn't search that. I was searching like, why is the rating?
There's one that again. Who ordered? Yeah. Because I guess there you have to be. Oh. Sorry, I also think like. Yeah. Or look. Yeah, right. Yeah, well, so would you? Right, well, this is, it's a confusion, so, there's a paper out here. Like years ago. Yeah. He's just. He's a person. I'm looking at it, just did a 40. Well, so this paper. So what is that? Get the. It's often true. But one of the things we did is they put all this. Hydrodynamic and all kinds of different systems with either rotating systems and field, creating all using some racks. I have drawings to that. So we did so we're gonna turn this into some long. And so it's all real. And I have ideas. And I said, you know, you should get like that. I think it's like, this is right. You know, the person just that. Yeah, I think it's true that's going to be had. You see books, I just think there's like why. Actually, transition. Why? Yes. Very nice. So it actually based on two ground points. Yeah. This point and then what is possible just
connector, USB.
We don't need dongle, so you have to just get on the Zoom and start.
Okay.
So just go to the guest network.
I think I have EDU Rome, so I have to remember the.
Still. Oh, right. Oh, yeah. But this game, the counter outside square inside. It's something that's inconsistent. I use that theory.
So don't log into the audio.
Let me get out of your way here.
Yeah.
Unplug.
Let him go.
Sorry.
Sorry, my.
I generate.
Yeah, just share the shadows.
So William Stock is at
4:30.
Okay.
So how do you pronounce Enkaleda?
Yeah, thankfully it's phonetic, but people have trouble. A lot of slides.
Can you transition it?
It controls this.
So just transition one slide. I want to check if that's.
Oh.
the right transition. Okay, good.
Yep.
It's working. Sometimes
I
it
mean, the
freezes.
bottom part will.
Yeah, it's all pretty relaxed.
Slides, but they usually go quickly. I just try to.
Civic College. My main campus is Civic College.
Yeah.
Yeah, I know Jeffrey Morris and like it's a shame even for us, even we don't talk. I gave a talk and I'm on their defense committees.
Right, like general.
I even wrote a proposal with Ilona. I don't know if you've seen that.
Energy extensive.
Yeah.
Excellent.
Janel's party.
Yeah, well, so.
I have them, I have all of this.
Yeah.
Oh, yeah, agreed, yeah.
Yes, I work on more formal aspects of it, like audio, but then you have a lot of questions and all.
Yeah, but maybe there's simulation, everything has to connect.
Yeah.
So I have a little bit, if I try to connect the two or something, it's still work.
Maybe we should kind of have you over at City College and. Yeah. Yeah, maybe in the first week of April or something. Okay, but I would say more to the committee, but it's like more undergrad. But then I think, yes, no, but I think you have more visual things, so they're.
You're thinking.
That would be great actually. Let's meet that time and then we can chat. Yeah, I'll send you an email. Perfect. That's a Wednesday between 4 and 1. Yeah, perfect. Okay, let's start. Okay, our next speaker is Enkaleda Lucy from New Jersey Institute of Technology, which is just a couple of NJ transit stations away from here. So, go on.
So, hello, everyone. I come from NJIT, and most interestingly, I'm a mathematician by training and in a department. So I come from a different background. I find these workshops very useful because I get to see different points of view, and this is where I learn a lot. So I hope not only you learn from this talk, but also I learn from you. So please, if you have any questions, get in touch. So I will tell you a little bit of the work I've been doing on microspinners, very largely defined. So I work on collective motion of motile agents, and you hear this a lot, right? Active matter, everyone defines it as self-propelling units that interact with others, right? This interaction will depend on the medium, on the type of unit, type of agent, and then you get collective behavior. Right? All this collective behavior obviously will depend on the interactions, the units, and right, the types of agents, right? But you get to see collective behavior at all scales, right? From bacteria, right, and algae, spermatozoa, all the way to the birds and fishes. So I specialize on the microscale ones because by background, I study hydrodynamics. So what do I aim to do? What is kind of, especially in the math department? So 3 aims. First is the modeling of the swimmers, where we try to build in the correct physics, not just self-propulsion, but include things like hydrodynamics, interactions with the environment, include the particular features of the swimmers, And most importantly, keep the model as simple as possible, but not simpler, right? That's crucial. Then based on those models, checking with the experiments, then there is the computational aspect of it, trying to make efficient computational models that can simulate thousands of these. And last but not least, and I personally find this very important, it's to compare with the experiments and validate that these models are doing something correct. And that way we can trust them. So what are the most modeled microswimmers? The ones that people everywhere go to, it's bacteria like Bacillus subtilis, E. coli, everyone has heard of them. They're called pusher swimmers because they push themselves forwards using their flagella. And as they move, they disturb the fluid flow. So you get this forced dipole fluid flow, right? There's no inertia there. We're at very, very low Reynolds numbers, so practically zero. And the fluid flow, you can see the streamlines coming in the middle of the swimmers, going out in the front and back. Chlamydomonas, so the bacterium is a eukaryotic cell, propels with two front flagella, so it pulls itself. So that's your typical puller swimmer. And the fluid flow averaged over the breaststroke, it's roughly the opposite, right? So mathematically, that's a sign change. Spermatozoa are also pushers. If you average over one undulation of the flagellum, and then we have phoretic swimmers. There's a lot of work on this, and we can make them pushers or pullers. And then there's collective behavior. There's been a lot of work on this. Right? You get collective behavior, and lots of people start to look at why is this emerging, right? So this is Bacillus subtilis, lots of continuum theories, lots of simulations, right? From rod-like with hydrodynamic interactions to the most prevalent, it's squirmers, so that's spheres with variable tangential velocity on the surface. And somewhere in between, that's my own, where you have ellipsoid swimmers, also with hydrodynamics. Right? So lots of these models, beads and springs, ellipsoids, various things, right? So these are all trying to include these multipoles. And the way I think about this is that you want to build a simple model, but if you throw in everything, that will make it difficult to simulate tens of thousands. The same way as if you're trying to draw 10,000 bulls, obviously you're not going to be able to draw in detail every single one of them. So you want to distill the model to the very, very specific, the minimal, right? So here the bull, for example, still has the horns, the legs, so that way you can still tell it's a bull, but it's simple enough. So what do we keep in mind about the swimmers? They live in fluid, not in vacuum. They swim and they disturb the fluid. This disturbance fluid flow affects the other swimmers there, right? So they are hydrodynamically interacting. And they do collide with other swimmers and surfaces. And the vast majority of microswimmers, vast majority, they're not spheres, right? So they're elongated or spirocate. And that turns out to be important. So I'll show you a model, a mathematical model, very, very minimal, tracing the center of mass and the direction of propulsion, right? So all this is saying is each swimmer propels on its main axis. It's ellipsoidal, can vary the aspect ratio. It gets rotated and advected by the fluid. There's forces and torques if it collides with others. And then what we do is that we add all of these force dipoles that each swimmer kind of puts into the fluid, right? So we're adding up all of these fluid disturbances in a way. So you say, well, that's minimal, not bad. My preferred method for this is immersed boundary method. And one can do this relatively fast. But one thing that this has special over the Stokesian multipole method is that this is versatile. The fluid flow does not need to be Newtonian or Stokes. One can actually adapt this to other scenarios which are more akin to experiments. Right? And also, we don't need to have the particles uniform and so on. So it's versatile. And this is good because we want to build methods that can be adapted to scenarios in the experiments. And sure enough, you get collective behavior, like 2D, 3D. And you say, well, many people have gotten that. So how do you check that yours is correct? Using experiments, which we'll get to later. But then there is an important thing. Swimmers in nature and in the lab, they're always in some kind of confinement. They're not in free space or periodic domains, right? That's a joke for theoreticians. So they're always in confinement, right? So from microalgae, right, to bacteria, above the surface in biofilms, spermatozoa also have to navigate the network structure, and even in industrial applications and in the lab, there's always some kind of confinement. So if you want to study these, then most importantly, if you're an engineer and want to be able to direct this, then you have to understand their motion and confinement. I happened to visit the lab of Ray Goldstein when they were doing one of these first experiments with active matter in confinement. So drop of bacteria, squash it between two plates. And if the diameter is within a certain range, they just organize by themselves into this kind of vertical structure. And you will see there is some edge, boundary layer, right, that goes one direction in the bulk, in the other direction. And this is stable for as long as they have oxygen.
But why are they not multiplying?
It's in shorter length scales. Right? And as you will know, bacteria, they're not thinking, right? They don't have a leader they follow. You can't exactly give them instructions they will listen to. So this is just mechanics, right? So collisions, fluids, right? So sure, we do simulations, right? You have swimmers and they will hit the boundary, right? And they will stay there unless something else knocks them off. And you will notice they swim at very, very low angle because also the fluid is conspiring to keep them to the boundary. Okay? So they'll follow the boundary as long as they can. Now you put more of this around. So now they have to struggle with the others, right? They have to push others out of the way, right? They will reach a boundary and there they have to fight. Now remember, these are elongated particles, right? Not spheres. So they do tend to align, right? Just due to the shape. And once they align, with their flagella in the back, they push fluid flow. And soon enough, you will see that a lot of them are lining up and start to circulate the boundary. And the other ones also will find a place. And you will see fluid flow emerging, right? All of this fluid flow, they're pushing with the flagella. It's in the opposite direction, right?
Probably going to mention this, but what is the model of the particle? What is
It's
the head doing?
the red ones?
Yeah.
That's just for visualizing how fast they go.
No, the head of each of.
So that's just to see the direction of propulsion, right? Yes.
So that's not any special point.
No, it's just for visualization.
I thought some bacteria kind of move straight, but then they stop and they tumble a randomized direction.
So we don't have the tumbling here in this model. And no noise. So this is just collisions, hydrodynamics, confinement. Right? One can include those, but to get this particular phenomenon, we did not include those.
What is the boundary condition?
So this one, it's because it's water inside, oil outside, so it's just a no stress boundary condition. So simple confinement, straightforward, from simulations point of view. And now what happens when you put many of these together, right? And remember, this is as dense as bacteria get, right? So it was controversial when it came out because everyone said, well, hydrodynamics shouldn't matter, right? It's very dense, it's screened and so on and so forth, but they're still in fluid. And soon enough, you will see at the boundary, lots of them are starting to line up, right? Because they're elongated and it organizes by itself, right? Very quickly. Once the boundary organizes and the rest of them organize quickly. Now, if you remember from the movie, right, we cannot tell which direction is the front and back of the bacteria. You cannot really see the flagella, not easy. So all you see here is that in the bulk, they're moving in one direction, but then they have a boundary layer in the opposite direction. The simulations are saying something different. They're pushing fluid flow with their flagella back. And if I hadn't put these black dots to indicate the direction of propulsion, all you'd see is that the ones in the middle are moving backwards. But really, just the fluid that is moving them backwards. So, the group of Ray Goldstein did new experiments to check that indeed that was the case, right? So this was proof by experiment that fluid dynamics matters. You want hydrodynamic interactions if you want to capture things correctly. And if one has simulations, one can turn on and off various aspects. If they are circles into the squirmers, they don't organize because circles don't align. They have trouble aligning, so nothing happens there. If you don't have hydrodynamics, you may get local alignment. In some cases, you might even get some motion, but definitely not the boundary layer. So one needs both. Different people took different messages out of this, but the message of the paper was that you need both the swimmer shape and the hydrodynamic interaction. So, but one can further improve these swimmer models, right? This one was just tracing one ellipsoid, center of mass, direction. Another way to do that is by tracing two beads, still pretty minimal, connected by a spring. One can do this with using Stokes sleds, right, for hydrodynamic interactions, or put this in the Immerse boundary framework. One thing people don't include, though, yes.
This is symmetric because when you have the flagellum is allowed to move and it breaks this parity symmetry, right?
The flagellum pushes on the fluid, right? And yes, they impart a force on the fluid.
Maybe the question is how do I differentiate these two?
One of them has a flagellum force.
Okay.
So it's two beads. One of them is the head, one is the flagellum.
Thank you.
But one thing people never include is that what do bacteria do? They counter-rotate their head and tail. So if we put this, and do the torque on this, and we can also vary the size of the beads if we want to make an asymmetric swimmer, and that becomes important to make a very, very minimal spermatozoon. Like if you cut across the swimmer, you have the force dipole. That's the dominant flow. But if you cut across these beads, you can see the effect of the counter rotation. And you will ask, does that matter? Well, let's take a look at two swimmers, starting the same, but here they have this torque dipole. What do you notice? They roll over one another and then completely go out of plane, right? So their kind of local interaction part is very, it's not forever, right? They don't align forever like a lot of the theories kind of suppose. So this has lots of implications, right, for coarse grain theories, right? The pair interactions are not just simple. I mean, that's what this slide is saying. So the local alignments are just for a limited amount of time. But where this becomes very, very important is boundaries. So if you have your typical force dipole swimmer hit the wall, it will just go straight, that wall. But if you have this counter rotation, it will circle about the wall. And that's indeed what bacteria do. Bacteria, spermatozoa, they actually go in circles at the wall. So if you care to catch this correctly, you want to include this counter rotation. And this is just a straight wall, but we can do things like obstacles. So method of images with a sphere. We don't have this torque dipole, like the swimmer continues on the same plane, but on the torque dipole, it gets deflected. You make the obstacle a little bit bigger. The swimmer swims alongside the obstacle, a colloid, for a little bit, and then it will scatter away, right? And of course, you still have this deflection. And most importantly, if your obstacle is big enough, the swimmer gets trapped, right? So lots of engineering applications, and you can see this with obstacles, with pillars. The engineers are already exploiting this to entrap or not swimmers, but the idea is with this torque dipole, you kind of circle a smaller circle around this colloid. And if the swimmer is inside a solid cage, it's the same idea, right? Instead of going around the equator, it kind of circles something small. So this is a model, and it's capturing something that you actually see in experiments, even with colloids. And the motivation is because now there is a lot more experiments with microswimmers in very complex structures. Things like, here's the group of Sujidata doing experiments with gel beads, kind of to mimic cell tissues and seeing how the migration of bacteria on this, it's a lot more complex than you could think, right? And also swimming in pillar forests. And there's also results that if you include a few colloids, depending on their size, it can completely affect bacterial speed and tumbling and so on. And so there's a lot of work on this, right? Understanding the interactions of swimmers, whether individual or collective. So we started doing continuous theory to include this counter rotation. And I'm throwing this here because we had talked before. So there's a lot of work here, right? So we have the fluid equations and we have the effect of this torque dipole. And can do linear stability analysis on this, pushers, pullers, so people coming from that community, this will ring a bell. What essentially we see is that microswimmer chirality decreases both the critical density and critical scale at which pushers, that's the model bacteria, that's where they have an instability. Pullers, they're stable, right? They're good. And of course, we include this. And then we started to do simulations of this. And it's just very difficult to find test cases for which to test, right? Because everything is coupled. So including the self-propulsion and the activity and decoupling those, it becomes a lot harder to kind of ascertain, but there's definitely a twist in stability. So, this is ongoing work, simulations of this. But this brings me back to some prior work and hopefully something that will resume. Spinners, just instead of counter-rotating, right, head and tails, just spinners. And in fluid dynamics, everyone will think of the basic singularities. You have the Stokeslet, the Rotlet, the Stresslet, and so on. And what is the Stokeslet? It's a very kind of order one representation of something sedimenting, right, in Stokes flow. So the Stokeslet is physicalization, right, order one of something sedimenting. Swimmers, those are stresslets, right, force dipoles. And in between you have rotlets. What are rotlets? Well, that's something spinning. Right? So a lot has been done, right, on sedimenting things and force dipoles and swimmers, but rotors, it's only in the last few years that experimental realizations, right, are being done on that, and the theory is catching up. So can particles with rotation, without self-propulsion, can they self-organize? So when we started this work, when I was a postdoc, the primary motivation was this paper because they looked at gears, very dense, and they spin on different directions and they can get different structures, right, as these gears interlock. It's like, okay, but what if you include fluids? And trying to simulate this, which we can do, it becomes a bit more difficult, right? So how about we go back something even simpler, spheres.
So you're putting them in ambient fluid?
Yes. So we put the spheres in a fluid and in a monolayer. That way we don't have to deal with 3D, or at least to understand things, but we can do, of course, 3D. The hydrodynamics is 3D. But even simpler than that, if you're a mathematician, you start to play with the equations. So to the leading order, it's a rotlet. And if you have everything in one plane and the torques, right, are perpendicular to that plane, you can actually write exactly the equations for the center of mass of the sphere. So you have 3D point rotlets, right? And you can do the math of this. Right? And we have kind of a spin. And this should look familiar to people that have studied vortex dynamics. And so that has been a playground for mathematicians and mechanical engineers for decades, still is. And in fact, you can carry out the same mathematics, right? You can derive the Hamiltonian, constants of motions, and in fact, it's so similar to the 2D point dynamics that it's uncanny. Right? It's just 1 power of r difference, but a lot of these are same. So what happens, right, if you have two spinners? If they have the same spin, they will co-spin about their center of mass. Nothing special. If they have different spin, they will co-propel about their center. Now, if you have three of them, and if you have an exact configuration like an equilateral triangle, or they start in a line, they will kind of maintain that. And in fact, three rotors, same spin, you can start them in anything, it's always periodic. And that just comes from simple math. Just you have so many constants of motions, right? All those conservations, and just like 2D point vortices.
But in 2D point vortices, n greater than 3 is chaotic, right? So
Exactly, and that's what we see here. So when you do 4, if you have an exact configuration, sure, right? That's good because the symmetry is that conservation. But but 4 or more, then you get chaotic motion. Right? So 3. And if you talk to fluid dynamicists, they say, well, chaos in low Reynolds number fluids, right? They get a bit, but it's there, okay, in this model. So as physicists, a lot of you will know, right? N-body problems, right? You know about sedimentation, you know about 2D point vortices, and now you know about Rotlets. It's just some interesting math on the side. But beyond that, of course, you're dealing with experiments, you have the 3-dimensional effect, confinement, and all of that. So in the end, to understand more, we do have to do simulations.
So this Rotlets is a you're looking at a 2-dimensional system.
So it's 3D fluids, but they are on the same plane, right? So it's just which is, I mean, for experimental reasons, it's not completely realistic. Yes.
So you're assuming that the points are being affected by the flow.
Yes.
Right? So
Right.
does that match the realistic experiments with bacteria? Is it actually entrained by the flow of the fluid, or?
Yes, and in fact, we don't even have to go to bacteria. We can talk about Skinner experiments that have been done, right? So as each particle spins, it moves the fluid around it, and the other ones can be affected by it.
Asking it like if there's any lag between, like, because if you have a particle in the fluid,
Oh, I see.
it has a mass, right? And maybe it doesn't.
Right,
kick
so
back.
here in the 0 Reynolds number, we're not talking about inertia, so the fluid flows, they're kind of instantaneous, right? Obviously, in experiments, you have inertia, and then you'll have to take that into account. But for our purposes, this is like long-range, instantaneous reaction. So this was a nice kind of math exercise, but of course, in the end, we have to do simulations to better understand. So if we put everything in the same layer and the torque perpendicular to this layer, and then try to see, it's the same immersed boundary method. So here is same spin rotors. So we start with something dilute, and eventually they will start to cluster. So smaller clusters, they start to become bigger, but there is kind of yes.
There's substrate or you
Just in the plane, but we can do this on the substrate as well. So you get these clusters, little bit higher density. You see the clusters start to be bigger soon. One thing you will notice, and you can compare to Williams' experiment, is in each cluster, the ones at the edge, they're spinning faster. So you get these clusters, and you can definitely see, in this case, because they're clockwise spinners, the clusters are spinning clockwise, and you have this edge current, right? And this movie is a little bit longer, because what happens is that eventually they merge into one large cluster, right? So you can even kind of do a back of the envelope calculation, how high the density has to be so that eventually they form one large cluster. And in that large cluster, right, you can see the edge currents, in this case, clockwise, and the fluid flows that go with it. Yes.
You're in 3D, so you have a campus or 3D together?
It's just 3D, so the whole thing is 3D fluid flow.
So you have a researcher in flow.
So this is just just Leonard Jones.
Okay, so
So
you have an
that-
attraction.
So a little bit, yeah. To keep them from overlapping. And so yeah, now it's you can see large cluster with the clockwise edge current. And yeah. Oh, okay. And this one is interesting. It's you increase the density even further and you see bubbles. Right? You could call them. So these are empty spaces, right, where you don't have the spinners. And you can see there that the edge currents are counterclockwise. Right? So that is an interesting concept thing. And even further, when you get close to packing density, then you get rotating crystals. So you get these domains that spin, and then the domain boundaries that constantly melting and forming and rearranging.
There are these starfish and Leo experiments, how they.
Exactly, yeah. So,
See
yeah.
the odd elasticity kind of thing.
I haven't checked in the old elasticity, but it's just like that. And we can do mixtures, right? So half and half, left and right spinning. At low density, you get the gas-like phase. You increase that, you get kind of this lane formation with the speed highest at the boundaries. Even further, you can get vortices that they rotate about the spin. And even further, you get mixed crystals of mixed spin, and then particles go in and out of this dynamic crystals. So, and one could even throw in some inert particles, spheres, and they get affected by the fluid flow. So nothing interesting at the gas-like phase. At the lanes and the vortices, the inert spheres like to be transported where the fluid flows are higher. And at the crystal phase, well, that's a bit of a mess, right? But if you're an engineer and want to use this for transporting material, you obviously want to be in those regimes. So I'm throwing this out, the summary and discussion. We're mostly looking at microswimmers. And what I want you to remember from it is that interactions between swimmers and a wall, they are not straightforward. They're not a simple rule. They're complicated because they depend obviously on fluid dynamics, the swimmer shape, and any swimmer particulars, right, the counter rotation. So that has implications, of course, for continuum theories. We strive to do models and simulations tailored to the swimmers, and particularly for complex environments, and also fluids, that's another talk. And if we learn to understand how they behave in this, then we can learn how to control their collective motion in such environments. And then there is this entire active matter of spinners and rotors, which is a very happening area, as you know, and there's lots of work, right, on that. So I will end with this, and thank you all.
Interactions with the wall, are they at far distances purely hydrodynamic? Usually.
Yes. Yes, at far from the wall, they're just hydrodynamic, but when close to the wall, there's also the direct collision.
And they're universally attractive, so they want to be.
It depends on the type of swimmer.
Ah.
So I only showed the cases of bacteria pushers, so they like to go near the walls, but there is the pullers, which go to the wall, but they can scatter away. And the shape there becomes even more important to capture this.
And if the swimmer is like a millipede with lots of tiny fluid, which is neither pusher nor puller.
We'll have to simulate that to see exactly, but but yes, exactly this. We cannot put them all in the same box, right? Say swimmers do this at the wall. It depends on the swimmer. So we have to.
Yes, I have one question. So the people have studied the coarse grain in vortex fluids. So is there any hydrodynamic theory of coarse graining the rotlets?
I mean, there is.
But I mean, your images look very much like the stuff that, when you got these one half, dislocate, disclinations.
Yes.
When, you had sort of things like that grow like that.
Yeah.
I think that's a signal of
Yeah, so we started looking at this, the continuum theory for the Rotlet dipole swimmers. And so that's work, it's ongoing, but away from confinement because it's complicated.
So if I need to think about macroscopic behavior of these local bacteria, they produce power. Can it be that you have negative viscosity or negative dissipative coefficients in such liquids which lead to
Yes, yes, there's been in experiments that measured this, and in simulations one can see. So bacteria, like for whatever food they consume, they put power into the system, and there is a decrease of viscosity for pushers, like bacteria. And for pullers, like algae, theoretically, they've shown that viscosity can increase a little bit, but pullers, they're a bit finicky with experiments. So with simulations, yes, we see that. We see the change in the viscosity.
I have one quick question. So do you see any new hydrodynamic instabilities that are only in active systems and that are not there?
Lots of them. I mean, speaking of the rheology, the rotors, one of the reasons people started to study this is because they affect rheology. So you put a few spinner particles, you rotate them, and you can make the flow go faster because you can lower the viscosity. So there is interesting hydrodynamics there, and obviously applications for engineers. And
Okay, there are no further questions. Thank you. Okay.